All right. Good morning, everyone. So let's go ahead and get started. I know that people are still coming in, um, but it's okay. All right. All right. So good morning and welcome. Thanks for coming here early, 8:30 a.m. in the morning, and I know it's been a long week. So uh, thanks again for being here after this long week of talks at IROS. So my name is Kaveh Fathian, and I'm an assistant professor at Colorado School of Mines. Recently joined, and I have the pleasure of organizing this workshop for you. And it hadn't been just me, so there's this team of amazing people that sort of helped organizing the workshop and sort of scheduling everything. So you see their names here. Not going to read them, but we have like senior people from academia, from government, Army Research Lab. We have junior faculty that helped a lot with logistics of the workshop, with submissions and sort of reviewing them. And as you see, some of them today, they're going to be chairing the sessions. So just a little bit about the workshop. So this is a follow-up on a very successful workshop that we held at ICRA 22. It was called Robotic Perception and Mapping, and it was very well received. You see the link to that workshop if you want to go and check out the talks that are recorded. The talks also are going to be recorded here today, so we'll be posting them on YouTube at some time in the next 2 weeks. So I think this workshop is also very well received. So on August 20, we got to learn that we have over 260 registrants for this workshop. So we're hoping to see them all today as we go through the talks. All right, so just quickly, what are the objectives of the workshop? So this is basically the same objectives of the previous workshop. What we really want to understand is where do we stand? What is the state of the art in robotic perception and mapping? And especially the past, I think, a year or two with this sort of huge success of machine learning, AI, large language models. We want to sort of explore that and see what is the state of the art and how is that going to impact robotic perception and mapping. Sort of go through these topics together through the set of talks that are given by our distinguished speakers, to whom we are very grateful for accepting our invitation and coming to this workshop. So we have overall 16 invited speakers and panelists. So we're going to have a panel. It's going to be 40-minute discussions asking some, I think, very exciting and interesting questions about the sort of connections of recent advances in AI and robotic perception. And so the talks are going to be 20 minutes. So we ask all of our speakers to try to keep their talks to 15 minutes. So we have some time for questions and then transitions. And this is, and before showing you the workshop schedule, so we have received several contributions, several papers that were, these papers were peer reviewed, and this is a list of accepted papers. The ones that are highlighted are the ones that were selected as best papers, just based on the peer reviews and their recommendations. And they will be receiving a monetary prize that's supported by the TC on robot vision. So these papers, all of them have posters that are outside of this room. So I highly encourage you during the coffee break, lunch break, to sort of stop by the posters and talk with the presenters. And that's the goal of this workshop. We want to make it interactive so that all the attendees and the speakers can sort of interact with each other. And these two best papers that are highlighted here, they're going to have 10-minute spotlight talks during the workshop. I have to acknowledge the sponsor of this workshop, which is the IEEE Technical Committee on Computer and Robot Vision. And you see their co-chairs and associate co-chairs here. So we're very grateful to them for supporting the workshop financially, and that's the money that will go to the two best papers, and part of the workshop logistics. All right, so here's the workshop schedule. This is also available on the workshop webpage that you see in the bottom. You can just go to the ROPM link that's in the bottom, or you can just scan the QR code there. If it's big enough for your cell phone to capture that. And yeah, this is posted on the workshop webpage. And just to go very quickly, so we're going to have 2 sessions in the morning, 2 sessions in the afternoon, and the sessions in the morning. So these 2 sessions, they all have these 30-minute coffee break and sort of poster sessions in between them. And I think the coffee will be right outside of this room. Session 1 is chaired by Chen Wang, and he's going to come here in a minute and going to introduce our speakers and share the first session. And Chen is he's an assistant professor at the University of New York at Buffalo, right? Computer Science and Engineering Department. Thank you so much, Chen, for chairing the first session and for being here and helping with the workshop. I think it's a good time to sort of hand this over to you. And yeah, if you want to come here. Yeah, so the last thing I want to say is that, yeah, after session 1, we have session 2 chaired by Golnaz, and then there will be the panel discussion for our lunch break. Okay.
Hey, hello everyone. Next, I would like to introduce our first speaker, Professor Konstantinos Alexis. So he mainly works on the domain of autonomy, perception, planning, and control. And his research has received multiple awards, including the recent win of Team Cerberus at the DARPA Sub-Team Challenge. Okay, welcome.
Needed our explanations. All right, so hopefully this will work. Let's find out. Yeah. All right, good. So I don't see what I'm presenting, but hopefully I can change slides, and that suffices. So first of all, thanks a lot for coming that early morning. I don't know for you guys, but for me this happens persistently when I first connect on a projector that requires changing resolution.
You're starting 1 minute early, so.
Well, it's fixed now. It just takes a bit time to update the resolution. All right. So thanks a lot for coming. Thanks a lot for actually being here that early morning. And I will discuss. I will start from the topic degeneracy, aware multimodal localization and mapping. Also, at the end, I'm going to present a new direction that we're working because it shares relevance with that, but I don't want to share with you. Although it's not about multimodality per se, and you will understand what I refer to. But let me start with ideas that if I was lucky enough to have you also in my keynote presentation, then you probably saw it a bit there. And it relies on the idea of and the concept of deploying robotic systems in areas that are what we will call in general sensor degraded or visual degraded if we just have vision in our minds. Right now, I mean, this is not actually a degraded environment per se. This is actually, some of them are relatively fishful environments in the vision sense, but they can present a host of different challenges. They can be self-similar, as some tunnels are. They can be very dark with less texture. In some cases, like Kaess, are like this urban setting that you see here. They can be filled with obscurance, such as smoke and dust. And sometimes, like here, for example, although actually there is pretty good illumination, so it's just the scale of the environment and the accuracy required in some of these environments that still renders the perception problem quite challenging. So I generally have this organization in my mind. How can we enable robotic systems to perceive and localize and navigate reliably in conditions, in environments that present conditions that are simultaneously self-similar, low texture, with obscurance, and so on and so forth. And I generally make the assumption that one of all these challenges is not present at any given time. Otherwise, of course, if we just degrade all sensors, then there is very little thing to do. And back in the day, when we started working on data training insurance, for which I'm not going to speak anymore, it's just old news in a certain sense, we worked on this cascaded approach of fusing modalities one after the other, and without saying much, it allowed us to do sufficiently well in the competition. But there were many limitations, and the two limitations that we had to deal with was, first of all, that we were tuning covariances by hand, which is a really bad idea to do. And number one, and number two, we had decision functions that allowed us to detect when each modality was degraded. So in this first work I'm going to present, we depart from hand tuning covariances, but we don't depart from the necessity of finding functions that allow us to detect when each modality is degenerate. And the next work we depart from that also. So here we now have a nonlinear factor graph. The fact that it's a factor graph is not really part of the solution. We're now implementing it, however, with the benefits of using factor graphs. And we have individual odometry sources, which are otherwise, however, calibrated based on the sensor noise. So we have a covariance estimation from each, and so on and so forth. And we are attaching constraints on the factor graph as LiDAR integration is being updated, or as, for example, visual inertial or thermal inertial odometry is being calculated. And to that end, we have these distinct factors that represent in-between factors from LiDAR or from any other odometry source, such as vision, for example. We have IMU factors, and of course, we also have any lamp initial factor. And the general idea is that we stack all measurements in a buffer. We wait in the buffer at any given time to have the ability to re-change the architecture of the factor graph even past in time. And we solve the optimization problem. In the general condition, this is just solved as nominally will be solved. But over a window, we address, based on the current observations and also a history of previous observations, if any of the modalities is degraded. And we address so by looking at the eigenvalues of the optimization problem for LiDAR, looking at the Hessian there. And we also threshold the de-optimality. And I explained some of these ideas also in a previous talk in this conference. Nonetheless, an important feature I didn't dive into detail at this point is that as we create a buffer of the measurements, it allows to deal with long-term degeneracy. In other means, if we detect a degeneracy because we see the odometry of any sensor failing over time and we see disagreement between LiDAR latency odometry and vision odometry, we keep a buffer that allows us to go back in time and change the structure of the factor graph we have built. And then accordingly, we also update the map we have constructed, for example, for LiDAR, which allows us to localize again correctly in the future. In other words, we have both short-term degeneracy handling, we're just removing a constraint from a sensor, and long-term degeneracy handling by changing the structure of the factor graph. And some of that you will see happening in this result here. So it's going to be two types of degeneracies. One that is self-similar degeneracy, self-similar environment, and this is what's happening here at this point, and method that only does short-term handling breaks. With long-term handling, although we had some bad measurements on LiDAR with the assistance of BIO, then we have correct estimation of the path and the map of the tunnel. And in the second case, my video gets started to play. Here we are just removing LiDAR point clouds, and we of course have, we have to rely on other modality fully here. Here we are relying on all 6 degrees of freedom on the other modality, whereas previously we were relying on thermal inertial odometry, visual inertial odometry, only for the degrees of freedom that LiDAR was failing, essentially. Or, in fact, in the factor graph, we attached all constraints, but the one that was prevailing from vision was only for the degree of freedom that LiDAR will fail. And you see here, of course, previous method doesn't have this handling to have failure in the map, new method, not having failure in the map. But I go relatively quick on this because I think that's also still old work. That was IROS 2022 or 2021, something like this. And I go to a very recent work that we completed over the last few months, which is about tightly coupling LiDAR with radar in this particular case, but the message is about actually the modalities at large. And the demo I will show is a robot that flies in a very smoke-filled environment that LiDAR is bound to not perceive more than 2 meters away, let's say, or 3 meters away. And we have implicit handling of degeneracy without the need for hand-tuning heuristic functions, which is a really bad idea, or without hand-tuning covariance. What are we doing? I'm sure you know the work of Long from Carnegie Mellon. We use the same type of features for LiDAR as Long had presented back in the day. So we have plane aligned features. We take the features, we attach them all in the factor graph. I know this initially sounds like a bad idea because we have 600 features from LiDAR at every observation on the factor graph, and one will think, but that's going to be computational expensive. But if we take all the Jacobians analytically and so on and so forth, this is actually no significant problem. We solve all the problems here that you see less than 100 milliseconds combined for LiDAR and radar being time synchronized, which is sufficient given that we are using in any case 10 Hz update for LiDAR and radar. So we attach at every observation 600 features from roughly, approximately, right, from LiDAR. And we also use velocity updates from radar because we have Doppler velocity that we can exploit, which means that the two modalities are actually, to use fake terms, speaking on two different languages. They are not, each of them for an odometry update. And then we have the error terms from AMU, radar, LiDAR, as mentioned. For each, we get analytical Jacobians to make sure that the problem is efficiently calculated instead of using, numerical derivation and so on and so forth, which is both expensive and less accurate sometimes. And the result is what you see in this particular demo. And I now have the opportunity a little bit to detail it in more detail before I go to my last point in this talk. So in this result that you see, it's so dense that, I think maybe if you get another wavelength of a LiDAR, you might still be able to see through. But given the 850 nanometers that we have, for example, on Oyster LiDAR, or approximately so, either first or second return is bound to be of very short range. And now, of course, this is the handling of the sensor. In fact, the measurement is just highly noisy. The sensor itself does not even report the measurement because it identifies this very noise. We've had also some exchange with people that are experts in LiDAR to understand this a bit more. And we colorize the map based on intensity, so it's not height or anything like this. At the end of the day, the message here is that on the x-axis, LiDAR is not informative at all. But we don't have to explicitly detect this. This is just embedded in the features as they get registered to the previous features collected so far in the chain, in the graph. And then we have radar, which supports localization going forward, and this is actually the modality that prevails in this direction. Now, once the robot exits this highly dense field area, LiDAR naturally will provide the most significant and most important constraints for the optimization problem, and this will happen relatively soon. I mean, you see, it's so dense that actually, first of all, it was difficult for the pilot to follow the robot, number one, and number two, it's actually a case that LiDAR is so degraded. Now, at this point, the robot just goes out from this corridor that we have blocked to make sure that we can fill it densely with smoke, and enters, the other part of the university, which is, it will soon clear as just some smoke just infiltrates the remaining area. And at this point, naturally, the solution, without any switch happening between modalities and so on and so forth, resorts, if you like, more into translating the LiDAR features and the LiDAR constraints coming from the plane and line features on the factor graph. Now, I'm not going to show the remainder of the video. The key message is that it's going to come back to the same spot as you would expect it, right, if localization works well. And a very similar result, albeit for different purpose, is in the case of self-similar tunnel, as this one, which is 500-meter long. That's it. I'm not going to show it all. You understand now here, LiDAR drifts slowly. It doesn't drift instantaneously. It drifts slowly in this self-similar tunnel, and it misestimates the scale on X, the main direction of the tunnel. Radar supports this navigation, and the combination of the two naturally gives an improved solution. Again, no need to play the whole video. I think the message is pretty clear. So I want to take a minute and depart from this, which is something that we have seen quite a lot of times, and go to something that I have a very significant interest. I had this interest when I moved to Norway, and you will understand why. So I think I have this observation after I relocated myself from the US to the Norwegian University of Science and Technology, and I'm Greek myself, and I had a lot of interest into why we don't see underwater robotic systems more ubiquitously used and more easily used in the environment. And beyond the fact that they are using necessarily a host of different sensors and so on and so forth, currently there are a lot of applications in what I would call confined underwater environments where vision should be sufficient because there's something to see in 10, 15 meters ahead of you. Naturally, you cannot do that if you're just navigating in the free ocean or anything. But there are a lot of applications for industrial inspection. Norway, just to give you an example, has a lot of autonomous underwater facilities for oil and gas. They're just there. There's no human or whatsoever. And I'm discussing with colleagues, and I see a different spirit in this community. They are experts in their domain, of course. Actually, they know very well what they're doing. But they have the custom to rely on different sensors. And vision there typically is there to just get data for the mission. And a second observation I had by looking at this community is that they do the very laborious process of taking the system and calibrating inside the water because they have to get the correct, refractive index and so on. So they use a traditional camera model and they calibrate it underwater in hope that effects due to the glass that you have for your cameras, if you're not using a dome especially, and of the refractive index are captured in the model. But I work with a very excellent PhD candidate, and we will have the results soon out for what you will see roughly here, a process that allows to calibrate your camera above water, as you normally do, without the laborious process of calibrating underwater, and estimating the remaining change of the camera model in a compound sense, so essentially another matrix that will multiply online where the system is underwater, right? And I think this gives, I related to this workshop for the following reason. This actually truly integrated vision most of the time. Here we are in a pool that is, I don't know, maybe 6 meters, 7 meters in width, right? A relatively easy environment. And we carry onboard illumination, but of course the water was not perfectly clear. The pool color is not ideal and so on, so it's very difficult to illuminate in these conditions unless you have a very big camera or something of that sort. And there's a lot of room also to go back into vision, if you like, and see how we can have more appropriate models, because actually we have change in optics, right, due to water and due to the glass we have in that. And I think we also went further ahead to present the idea that we can have operation by changing media. This means we can go up and down in water. And I don't think there's a need for a robot that goes out of the water and enters again into the water. And this, of course, in a very simple environment, there's a lot of features. But I want to share that I think the vision that we have is what I'm putting in this bullet point, which is that we could have, in these confined environments, autonomy much analogous to what we see on area robots. I have worked a lot of my years in area robotics, and I think that's the vision I will have for this type of environments, also for underwater systems. Last point, we open source what we do. We try to hire a lot of people. Thank you. Happy to take questions.
Okay, so thanks a lot. Next, we will take the questions from the audience. So, please.
I just have a quick question. What was the radar and which way did you point it?
It's a Texas TI AWR, so that's roughly, I should remember the field of view, but less than 90 or so, and it is 13 degrees pointing downwards, much like a traditional camera here.
I have a question related. Did you use the CFAR points from the radar, or did you use some other kind of output from the radar?
We use just the default points. We have worked on both. In this work, it's just the default vanilla output of the TI drive.
Okay.
Thank you. And any more questions?
So, what kind of onboard metrics do you use when to get the accuracy of your system when it's running onboard, like without any ground truth?
What type of onboard?
So, when your system's running on the device, what kind of metrics do you use to see how accurate it is, like with the absence of ground truth in those cases?
I mean, onboard?
Yeah.
Onboard, I mean, of course, the robot onboard doesn't really have any correct idea on its own. I think what the effort that we do is make sure we have a principal model for noise modeling, right? And then, so long as you do that, and all your covariance span from the noise model, and through the equations of motion, then I think that's the best we can do at this, or at least not the best we can do, the best we do at this point, right? But there is no esoteric understanding it is really potentially drifting. It still could drift, right? I'm not claiming that the robot cannot drift. Good.
Okay, and
yeah.
One of the problems with this execution is being able to balance the uncertainties with the consensus so that they're perfect weighted. You first have the LiDAR or the radar. These LiDAR.
So of course there is one aspect which is essentially kind of it's the elephant in the room, but then the formulation does not specifically address it, which is, do we have extra noise due to bad data association, right? Now this is not there in the formulation, right? The formulation at some point makes the assumption our data association is correct. The rest, given this assumption, can come from noise modeling. Now, is this assumption true? No, it's a classical discussion. You have a PhD candidate who spent all the time about trying to do this process formally, and then the main cause of concern is still data association, right? Which is not modeled at all. So this is a problem. This we should invest on finding out if this is happening and adaptively change our covariance, for example, or have better outlier rejection. In the process of doing so, we found actually a lot of issues on certain at certain oblique angles, and how LiDAR measurements are taking place, and we try to improve a lot in this direction so that this assumption actually holds more in practice. But errors and noise errors introduced by weak data association are not handled in the formulation. The rest, I think, is handled pretty simply. All right? Good. Thank you.
Okay, thank you. Next, I would like to introduce our next speaker, Katerina. She is an assistant professor at CMU, and she is interested in building machines that understand the stories that videos portray. Sorry. And mostly in using videos to teach machines about the world. So let's welcome Katerina.
So I would need an adapter because actually no, I think it works. Sorry. Yes, thank you very much. Good morning. Thank you for organizing this workshop. Thank you for giving me the opportunity to present my work. So I will discuss about some efforts that have gone on for the last few years in my lab on multi-view integration of visual information for autonomous driving and some recent work we have on manipulation. So here's an image, and we see a cat behind a fence, and most of computer vision models take the image and featurize it and predict labels for the visible pixels. And the results are reasonable. Like this is a result from DETIC, this DETIC paper from OnArchive 2022. We have open vocabulary 2D detectors and so on, but we know that this is very incomplete understanding. We know there is a whole 3D scene behind the image, and we humans are very good at understanding the scene behind the image as opposed to labeling the visible pixels. So in my lab, trying to capture this, trying to do inference of the scene behind the image, we said we need a placeholder, first of all, to capture that scene content. So we instantiate those three-dimensional placeholders. They have 3 special dimensions and multiple channel dimensions, X, Y, Z, and the number of channels. And every grid location has a feature vector, okay? And here you see them mapping from the video to those 3D feature vectors. And we, had proposed that back in 2019, differentiable networks to take the 2D images and map them into those 3D feature maps, okay? And these 3D feature maps can be optimized end-to-end for discriminative tasks like detecting 3D bounding boxes, and they can also be self-supervised just by predicting what the agent will see from a different viewpoint. So here you see the sequence of images just to show you how it works. Essentially, this neural network marries SLAM and deep learning. In a sense, there is a SLAM going on in the heart of the network. We take every frame, we know the camera intrinsics and extrinsics, we unproject the features into these 3D feature maps, and when the new frame comes in, we estimate the camera's 3D relative pose and translation, and we undo that so that we register feature content on that 3D feature map. All right. So the 3D feature map essentially is keeps the eco-stabilized features across the video frame. And of course, you can train that system end-to-end. It's end-to-end differentiable. It's all the way differentiable using the chain rule for any supervised objective, like detecting objects. But where we're most excited about is to train it self-supervised. So what you do is you go to a new query viewpoint, you see the image, and you reorient the map and project it down and map. And this worked very well and gave a boost over just training the network supervised. So the same ideas we have recently used for building bird's eye view maps and mapping this bird's eye view map to pixel labels. And I would say that these type of architectures now are, de facto, choice for self-driving cars. So here you see, you get good numbers using this very simple differentiable arm projection, which you can stack with LiDAR and radar features and get an extra boost. And, this is a part from Andrei Scarpathy talk a couple of years ago that shows that when you have multiple images, what used to happen is you try to first infer the labels and try to integrate the labels across the multiple views, and you'll get these artifacts on the bottom to your right. But if you first featureize and integrate the features first and then predict the labels, then you have persistent, nice 3D geometrical aware label maps that you can drive on. So I would say this type of architectures that take multiple views and featureize them and then integrate them using geometry are being used right now. In self-driving cars, they call this the vector space, which is very similar to what we say here, the 3D feature map. Okay. So this is great that 3D perception is actually being used for the most intelligent robots, I would say right now, are the vehicles, the autonomous vehicles. So given that this has been so useful for cars, what about robot manipulators? Okay, can we do similarly well using the same 3D inductive devices for robot manipulation? For tasks like put the fruit in the bowl and open the oven, and so on. So most of the tasks that I will present today are quasi-static, but this is not a limitation of the architecture that I'm going to describe. So what recently, like about half a year ago, we started thinking is that given that those architectures worked for self-driving cars, what about if we try to break the state of the art, like surpass the state of the art in robot manipulation, and the problem with robot manipulation is there are no real data you can use to compare. There are only benchmarks and simulation. So we used RL Bench, and we proposed an architecture which we call Act3D, which what it does is it takes images and depth maps from a set of poses, posed images here. The extrinsics and extrinsics, and it assembles and then predicts the next 3D key pose of the robot. So many manipulation tasks can be cast as a sequence of sparse 3D key poses of the robot's end effector. So basically, what you need to do is to estimate the 3D translation and orientation for the robot. So our architecture looks like this. We call it Act3D. It takes an image. So it's a neural architecture for multitask robot manipulation. So you should be able to train one model across multiple different tasks. That's why you also take the language description of the task, so the network knows what you want to predict. So you have your different viewpoints and depths, and you featureize those, and you aggregate them into a 3D feature cloud. So we don't need voxels anymore. We're only going to use points, and every point has a feature vector. That's why we call it 3D feature cloud, not 3D point cloud. Okay? And if you wonder what are the colors there, well, you take the features, you do PCA, you keep the three most important components, and then you map those to RGB, and this is how you visualize this 3D feature cloud. And then what happens is one big challenge once you try to put the 3D inductive biases into manipulation is that although in driving you can get away with a bird's eye view map, essentially a 2D map, here we do need a 3D map because we need to know exactly where the robot gripper should go. And not only this, but we need very, very high spatial accuracy. And then the standard way to do it is, let's voxelize the workspace, right? And then we'll have voxels, and then we'll do big self-attentions. Well, these self-attentions are going to blow up. They're quadratic on the number of voxels. You really need very tiny voxels to be accurate. So essentially, that's the main problem, the computation in a 3D feature space. Now, the previous here state-of-the-art per act, I'm not sure if you've heard this method, perceiver actor, essentially gets away by not doing these big self-attentions, but rather some, low-dimensional attentions, which unfortunately do not keep the spatial disentanglement of the features. So here is what we did. Instead of just having vanilla, self-attention layers between all point features, what you do is you do coarse-to-fine attention layers. So you start by sampling a 3D point grid, and then featurize those points by cross-attentions to the lifted 3D point cloud that I showed you earlier in the previous slide. Then you evaluate each one of those points about where is the gripper, and then around the predicted gripper location, you featurize again in a much smaller ball, right? You sample points in a much smaller ball, you featurize them with cross-attentions, you score them, and featurize again, and so on, till you find the point of, the final point will be exactly where your end effector should be, okay? So it's trained with, you train all these layers, of course, to find attentions with softmax, and then you also predict the continuous rotation. So there are very important details here of what these attention layers are. You very much need your network to be translation invariant, so you need to use relative position attentions. Essentially, this means that how much one point feature will like another should not depend on their absolute locations, but only on their relative arrangements. So this means that where the coordinate system lies should not matter in the architecture. So this gives a very, very important boost for the system. So this is the benchmark that we used, RL bench. And the results are that this Act3D is currently the state of the art. Not only this, but it also outperformed all previous methods here, high former and instructor-L by a big margin in the tasks that they assigned, but also per act, which is the previous state of the art in their own, much harder benchmark that they designed. How hard the benchmark is how different the test set is from the training set. Many times we devise a test set simply by moving around the objects, okay? So in that second test set, essentially, not only the objects are moved around, but also the objects are different. And what you can see is Act3D can do better than per act with only 10 demonstrations, while per act is using 100 demonstrations. So this is a very simple, imitation learning setup, learning from demonstration. We want to be able to have highest accuracy with a minimum number of demonstrations. So this is some of the tasks that we are attempting, okay? If you want to know what are the persistent challenges in this architecture, they are the follows. Although the way we score the 3D workspace to find the gripper can handle multimodality, which means there are many possible locations for the gripper to be, it doesn't handle multimodality in rotation because we use regression loss. And second, we still use a very simple motion planner to take us from one key pose to another key pose, okay? So the question is, can we get rid of that motion planner? Now, in our next work, which we call chain diffuser, we don't use a motion planner to go from one predicted key pose to the other. We actually, train our own model, a trajectory diffuser, to link those two key poses, okay? Now, before going to that, let me show you some very important ablations to see what matters in the architecture. Why we want 3D inductive biases and mapping? Because now test time you can change the camera viewpoint, as you see, and the Act3D model will still perform reasonably where any 2D policy, all these things that you hear, RT1, RT2, instructor-L, and so on, that they're very much dependent on the camera viewpoint. They cannot generalize to different views. So this is number one benefit. The second important thing is what I told you, that you need relative positions. You need to make sure your architecture is translation invariant. And second, I showed you coarse to fine attentions. We use exactly the same weights, the same transformer weights in all of those layers, coarse, finer, and finest. So this is very important to avoid overfitting. And other things is, as you see on the bottom of the backbone, now you can use pre-trained features. Right? So the fact that you are 3D doesn't mean that you're not going to use the features of the images and you're just going to use point clouds. No, you're just going to take the images and featurize them and specifically use the clip pre-trained feature and unproject the features, and you can still fine-tune the whole thing end to end. But you have a very good starting point in this way. So I think this is the most important things. Now, the cool thing about sampling points is that test time you can sample even denser points, and because every point is featurized independently, you can, have an extra benefit because at this time you can pay more to just sample more points, while at training time you don't need to do that. Now, the same way you learn from simulation, you can learn from the real world, what you see here. And as I said, a handful of demonstrations suffices. I told you that Act3D relies on motion planners, so how can we also get rid of these RRT planners as well from the whole picture? So here's what we did. Very similar architecture, again 3D translation invariant, one up projecting 3D feature clouds and so on. The only difference is that we have as input also the predicted key pose of Act3D, and then we train a trajectory diffuser, okay, trajectory diffusion model to take us from the first key pose to the target key pose. And this, did very well, and much better than the motion planner. The problem with motion planner, by the way, is that, for some tasks, for example, close a door, you need to allow intersection with the 3D point cloud. For other tasks, when the gripper moves in empty space, then you need to say, take care of not bumping into 3D construction of the scene. Well, now that you have a learning-based approach, you don't need to make these hard choices, okay? So J-diffuser, which essentially Act3D plus this trajectory diffusion, does as well as Act3D on most tasks, and those few tasks that actually fail, not because the predicted key poses are bad, but because the motion planner doesn't do a good job on linking them, it also does great in those. So what is next? It's unclear why we would we would care so much about handling multimodality while linking key pose to key pose, but not on predicting those key poses. So this is our latest work that will be on archive probably in a couple of weeks. We call it 3D diffuser actor. It's exactly the encoding architecture that I told you. You featureize multiple viewpoints and lift them, but instead of using softmax and regression losses to predict where the gripper is and how it should be rotated, you use a diffusion model. And this is very important because some demonstrations are very multimodal. And we know that regression losses really, really fail in that case. And indeed, this 3D diffuser actor does much better on predicting rotation than our Act3D. So just to show you the results, essentially, although this is work in progress, we have a plus 3D absolute performance boost, while Act3D had plus 26 over per act. This one has absolute plus 13 performance boost over our previous work. So I'm very excited about this line of work, of course. Yes, and we do very well both with respect to 3D models, our own, that doesn't use diffusion, as well as 2D models, like 2D diffusion policy, that don't use 3D encodings. And this shows the importance of 3D for manipulation, much, it was important for, autonomous vehicles. Yes, so this is the end of my talk. Thank you very much, and I'm very happy to take your questions.
Okay, yeah, thank you again. Any questions? Yeah, please.
Yeah, very good. So the question is, how are these models trained? All models, our models and baselines, are trained with essentially behavior cloning. You have the access to the ground truth actions. It's learning from demonstration. There is no reinforcement learning here. Yeah. We vary the number of demonstrations. So you want to know for different number of demonstrations the accuracy. We try 10 and we try 100. Yeah. It's 10 per task because it seems to be multitask. It's a multitask. So when it's 10, when it says 10, it's 10 per task. Yes, exactly. Sure.
Okay, we can take one more question. Okay, so if no questions, let's thank Katerina again. And next, I would like to our next speaker, Ge Yang. Ge Yang is currently a postdoc fellow at MIT and NSF Institute of AI and Fundamental Interactions. So Ge works on the reinforcement learning and autonomous robots with an emerging focus on spatial perception. So can I start?
Okay, cool. Thanks. All right. Hey everyone. My name's Ge. I'm a postdoc currently at MIT in the physics program. Today I'm going to talk about feature fields for robotics, and I'm going to talk about specifically language-grounded perception and mapping at multiple different scales. Okay, so before I get into it, first I want to talk a little bit about generalization.
So I think generalization is a phenomena that happens at like a larger scale. And even though we usually care about like the type of mistakes that AI systems make in our individual cases, but it isn't effective of a larger scale. And when we talk about larger scale, it's actually good to actually look at like what Amazon does in their fulfillment centers. So I want to lead with this question: how many different products do you think Amazon have in their warehouses? Okay, so I did a quick search on ChatGPT. Sorry, that's a joke. I did a quick search on Google, and it's roughly like 12 million SKUs. And this 12 million doesn't include the products from the 1 million third-party sellers. And if you include the 1 million third-party sellers and their goods that they house in their warehouses, this number goes up to 350 million. So this type of scale necessitates. Okay, this type of scale necessitates automation. And indeed, if you go to this entire logistic chain, there's a lot of robots and automation. But then if you dive a little bit deeper, like there are all of these places where they have still humans in the loop. Let's take this particular task, for example, picking. This is actually a pretty difficult task. If you look closely, you see that the task is so difficult that Amazon actually has augmented reality to help the person identify the correct bin so that he doesn't have to go up and down to search for the correct qubit to fetch for the object. A lot of the times the objects are also behind other objects, so you really have to stick your hand into the qubit to actually find the right object. The reason I want to talk about this is because on average, each one of these pickers can do about 300 to 350 items per hour. And now if you count how many hours it'll take for one picker to actually go through all of the items that Amazon has, that's like about 6 magnitudes of difference between like the time we have in this short video and the total number. So most of the product these people see on a daily basis are products that they have never seen like at work, and in fact products they have never seen in their entire lives. But when humans are able to do this. So to motivate this talk, I care a lot about generalization, and in particular open-ended generalization. And you can think about this talk as a talk on ingredients of open-ended generalization. Okay, so I'm going to talk about 3 things. This is the first things. Distilled feature fields enable few-shot language-guided manipulation. So in this project, we actually look at few-shot imitation learning scenario where our robot is given like a few items and demonstrations on these items for grasping. And then we expect the robot to generalize from these few demonstrations to like arbitrary objects we find like anywhere, either from our Amazon collaborators or from random rooms in our lab. So our key idea is that foundation models that are trained on 2-dimensional images from internet scale data sets contain a lot of rich priors and common sense. And we can actually combine these 2D foundation model features and use NERF or near radiance fields to lift these 2-dimensional features into 3D. So our method, our general approach, is called feature fields for robotic manipulation, or FIRM. And FIRM contains three components. The first component is a way to produce 3D feature fields in an automated fashion in the robot manipulation setting. And the second component is how to actually use these features for few-shot manipulation. And finally, we also demonstrate a way to incorporate language guidance in few-shot manipulation using these feature fields. So let's first talk about how to produce these feature fields. So here's our setup. We mount a small camera. This is a real sense, but we only take the RGB input of the camera, not the depth. And then we have the robot use a selfie stick to collect like 50 images. We can use these images to build a NERF. And this is what we see like as a NERF like built from these images. You can see the geometry is very highly detailed. So instead of like just rendering pixels, in fact we here first pass all of these images, like in the previous talk, through like foundation models. In this case, we're using Dino. And we have the near radiance field reconstruct the features. So here if you look closely, this representation, the 3D feature field, in this case a Dino feature field, actually has really well-defined geometry as well as really good separation between objects in the background in terms of semantics. So this paper is about trying to play with this representation and see if this will be the representation we use that generalizes both geometrically and semantically, and whether we can use it for manipulation. So how do we use it for robot manipulation? Many tasks can be many robotic tasks can be represented by 6 degrees of freedom, like grasping pose. So in this case, we let's take this mug for example. We first convert this mug into a feature field, and then we randomly sample these points from canonical frame of the gripper, and then we collect the features sampled at these query points and concatenate them together into this embedding that represents our demonstration. And then during test time, the robot is given a novel scene. And we run optimization to try to maximize the similarity between the grasp proposal and the demonstration. And then we pass these grasp proposal to a motion planner, and then we get we select top 10 grasps and then pass it to a motion planner to actually to execute on the robot. And then to enable language guided manipulation, we use cliff features instead of dino features. And in this case, let's take this query for example. I want the robot to pick up a bowl. Now, the interesting thing is that the robot has never seen a bowl before in the demonstrations. The closest thing it turned out that is a mugs or water jugs. So we first pass the query through the text embedding of cliff, and we get this text feature. And then we compare this text feature against all of our demonstrations. In this case, we only have 10 demonstrations for this entire example. And then we find the demonstration that's closest, that's the most similar to my query. What's interesting here is that for the query of picking up a bowl, the closest example we found is actually the demonstration trying to pick up this water jug. You can see that they're actually from different object categories. Now, using this demonstration retrieved using language, we can now run a similar optimization process, and then we can use optimization to find the top 10 grasps. The interesting here about this example is that you see there are two jugs in the back that are very similar to the demonstration we selected, while our robot is able to select the blue bowl in the front. So for more details, you can look at the paper. It's very simple. Okay, so here's some results. Here's Willem setting up the scene with random objects. And the first item we're going to ask, and the first thing robot does is I pick up this wooden selfie stick. The selfie stick was actually the idea that started this project. It was a joke. Okay, now we'll build a nerf, and we can also visualize the principal components of the cliff feature field. Notice the colors are a little different, and the definition is also different from Dino. Dino contains a lot of part level dense correspondence, whereas a cliff has much better categorical separation between the different vectors. Okay, so first I'm just going to ask the robot to pick up Baymax, and this is the same Baymax from a dense object net, which is still different Russ's lab. And it's also a distribution object because in our demonstration set, the robot has never seen a Baymax, but Cliff has seen a Baymax on the internet. So we run we visualize the attention of the robot using this heat map. You can see it's a very dense attention. We don't actually use any object priors here. And then we execute, and then oops, I think I ran over too quickly. Okay. So we can also the thing that a lot of people care about in the field is the ability to actually tell objects apart by their material properties or by some kind of physical properties. In this case, let's start with something simple, just colors. We have two different screwdrivers, so a red one on the left and we have a blue one on the right. Here I say pick up the blue screwdriver, and my robot is able to pay attention to the blue screwdriver. And then if you let the robot run its course, it picks up the screwdriver correctly. The geometry is pretty small, and if you want to pick up on the stem of the screwdriver, it can also do that. Now there's another one that I mentioned earlier. This is actually the actual experiment. So here I want the robot to pick up the bowl. You can see that it pays most attention to the blue ball in the front, even though the two objects in the back are actually very similar to, actually like from the same category as the demonstrations. Throw up because of the bowl. And when people are visiting us, like someone just put an AirPod in front of the robot on the table in front of like 30 people watching our live demo, and our robot just picked up. It's pretty neat. And here we have a red screwdriver, and the robot also picks it up. At the end, there's a felt like a blooper, but you can take a look at that example on our website. Cool. And I don't know if you folks noticed, there's actually like a transparent jug in the back that's pretty difficult to see. But if you have like a feature vision as a robot, you can actually see it very clearly. So this heat map indicates like the robot actually like notices that's the correct object. And when execute, the robot picks it up and put it into the bin. One thing you notice is that we don't actually update the feature field as we go. Like the objects still remain in the representation. So like trying to actually get this thing to work faster and like require much fewer images is something that we're actively working on. Cool. So this is the first part. To summarize, we designate novel objects to manipulate via language. And for this entire experiment, we only use 10 demonstrations over 4 object categories. And these are the 4. And these are the objects we demonstrated as like the test items. Okay. So we just did something on tabletop, right? And we built like all of these really nice graphics tool chain so that we can actually like visualize and do our experiment. What about like, can we actually like scale this up? So one thing we like that always surprises people when you tell them that our system actually scales up to a fairly larger scale is that they thought it was just tabletop. So let's like start with a table we found in CSAIL. Now, if you zoom out, you can actually use the same pipeline to build a map of this stairway area. And now we can actually type in text queries. You can ask people around the lab to actually say, hey, what do you want to find in this area? And here, let's say I want to find like lamps. And boom, you got like the lamp cycle selected in this feature field. And this is actually my favorite example because I didn't come up with this example and someone just like tried trash can or trash bin. And then notice that there's like a little thing on the right corner and there's an occlusion. Now, like if oops, that didn't run. Okay, that was my favorite example. I'm gonna show it. Okay, let's see. There we go. There we go. Okay. So I think I'm going to zoom in. Yeah, you can see this hiding behind. And now I'm going to zoom in. You can imagine this is a live demo, so a little bit slow. This is also like our viewer from like a couple generations before, so it's a little slower than what we have now. So now you can zoom in, you see like very clearly there's this trash can hidden behind the stairway with proper occlusion of the rails in front of it. And I can actually reduce the opacity of the shade and you see the trash can. We're planning on releasing like a visualization framework that combines like a 3D geometry, like a nerve rendering, and hopefully like Gaussian sliding down the road. It's already public, but like the public version doesn't have all of the features yet. Cool. So what we're doing here is effectively building a map, right? But like the map can also like can actually use it for other things. Internally, you can use it as a simulator. So I had a little bit of fun here, actually extracting like a high map from the model. And then you can actually do like real-time relighting. that was like a couple of days of fun work. And if you pour this into Isaac Gym, you can actually use this to train the robot. And the nice thing about like Nerve, about like these models we built, like the digital twins of the world, is that you can actually do a lot, you can actually change it on the fly. So you can see like me changing the height, and you can also see like how the thing looks like from the stairways perspective. I'm just going to skip over this part. And this is actually Isaac Gym, like a dog running Isaac Gym being visualized in our web-based viewer. Yeah, you can use it as a simulator. Okay, So now we have a tabletop experiment, and we show that we can actually cover the entire floor using the same pipeline. Like, can actually go bigger. Like, can actually go from the entire a floor to the entire city. So this also started kind of like a joke, because we realized that Nerf actually scales really well, especially for static scenes. So it turned out that if you just buy these off the shelf a consumer 360 cameras, and if you have a really motivated high school intern, you can actually build a map. So this is what we did. We mounted a 360 camera on top of a car, and then I wasn't there because I was busy that day, and they drove around Cambridge. And here are 2 example reels we took in Cambridge, and you notice there are 2 really nice ice cream shops in the corner. So if you take that footage and then just try to train Nerf using it, and this is the result. So you can see there's still a little bit shadows of cars on the street, and those are pretty easy to remove. You just need to identify cars and remove them from mass them out from images, and then you get a pretty nice a Nerf like this. In fact, you can also scale this up to cover much larger areas. And here's C-Cell. And if you're lucky, you can even capture the other side of Cambridge. You can see Boston. Cool. So to sum everything up, here I talked about neural fields for perception and mapping. And for tabletop environments, we have a plausible way to enable open-ended generalization by taking advantage of language. And then for indoor scenes, it turned out that Nerf has a pretty excellent scalability for building indoor maps. And then for outdoor scenes, we only need 2,000 smaller Nerfs to capture the entire Cambridge. So you could actually scale it up to city-sized areas. Now, what lies ahead? Here's a video my undergraduate research assistant Alan took yesterday of our robot. This is a walking policy trained with reinforcement learning. And if you want to apply our perception system onto the robot, there are a few problems. First of all, can you actually get the system to run at real time? And then second, we have different representations for navigation and for manipulation. Is there a way to actually have a single unified representation for both? And also, can this type of representation enable human machine and human robot interactions? We actually have something in that direction right now. And also, if you are generating individual features, for example, Clip or Dino or Dino V2, can you actually use this scene representation to interface directly with multiple different downstream larger models? And my take is that with all of these advances we have nowadays, maybe we already have all of the pieces to actually build the infrastructure and the intelligence for these autonomous robots to actually operate fully autonomously and do useful things in complex urban environments. Okay, that's the talk. I'm also on the job market this year. They told me not to say I'm also on the job market this and next year. My name's Ge. That's my email. Thanks, everyone. And these are collaborators.
Yeah, thanks again. And any questions for please?
Cool.
Hi, thank you for your talk. It was very inspiring. I'm wondering about these feature field maps, if they use a similar learning process to NERV, and in that case, does it make sense? Because as far as I understand NERV, it comes from the Graphics Society. It puts a lot of importance on appearance and this volumetric rendering. So does it make sense to keep learning features in the same way, or are you exploring, or do you have any ideas about different optimization, I would say, methods to learn feature-based fields?
Yeah, that's a good question. So the question is, does it make sense to actually use the techniques from a graphics community, and are there different ways? The original the title for this talk was actually graphics techniques for robotics, but then I played with a bunch of different things on that one instead. So I feel like we can actually learn a lot from a graphics community, because a lot of the graphics were actually inspired by physics. Yeah. This year, Gaussian splatting came out, right? And if you look at Gaussian splatting, our experience with these feature fields is that you don't want to use the photometric loss together with the feature reconstruction. You want to use the photometric loss to actually recover the geometry, and then the feature is something you distill on separately. And now, why do you have to use NeRF, right? Why can't you use Gaussian splatting? Why? And is there a way to actually have a unified representation that goes from individual Gaussian blobs that represents object poses to a appearance model that involves millions of points, right? So I feel like there's a lot we can do, and we just got to play with all of the different options. And this is just the model side, and there was also system side, right? For the robot, we have a previous work called a neurovolumetric memory, where we get a robot dog to actually jump between pillars and go between to actually go upstairs using internal 3D representation that's SE3 equivariant. If you think about NeRF is basically a generative model, and a view interpolation is basically a generative process. Right, so it's not very different. It's just the same I/O. You can put different things in there, and for different system requirements. Yeah.
Okay, thank you.
Yeah, sure. Thanks.
Thank you for the talk. So it requires a setting map pre-built from the data. So how can we to operate in an urban environment? There are a lot of dynamic objects. So how can you deal with the dynamic scenes with moving objects or something?
Oh yeah. So for a map, you can actually statically build it or filter out moving things. And then for onboard perception, you definitely need something that's working at real time. So we're trying a generalizable NeRFs or generalizable feature fields. But Gaussian splatting's out, so maybe we can also try that. Yeah.
Thank you.
Hi. First of all, I want to say great talk. I wanted to kind of go back to your example with the Amazon picker. In that example, I think it's reasonable to say one way to command the person is say, oh, go pick up this object from the bin that's second from the top left, right? And so going back to your example, the tabletop demonstrations, if you have a scene with multiple objects that have the same appearance, have you tested or do you have an understanding of how well it can reason about the spatial awareness?
Yeah, it's actually really interesting. So the reason why language is good is not because it gives you specifically what you want. It's because you can actually iterate on top of that to get what you want. So we had this a demo I did where we have a yellow rubber ducky and a yellow kind of spherical toy, and I was like, okay, I want a toy duck, and it didn't give me a toy duck, it gave me a yellow thing, or the other way around, and then quickly you can just modify the negatives to actually filter out the things you don't want, and then end up with the ones you want. So I thought that was pretty neat. Yeah.
I see. So in that example, even though it couldn't distinguish between the yellow duck and the yellow ball, if you gave some additional instructions to tell it to get the yellow item on the left,
yeah.
you could?
So specifically the reason is because the clip is trained as a bag of words, and for a scalability issue, reasons. And when I say give me a yellow duck, it kind of puts it depends on the relative amplitude of the features. It kind of biases towards the color as opposed to the object category. In that case, it's a problem due to the 2D representation itself. And one really interesting thing we found recently, we're trying to build a city that talks. So that the scene's actually generating text instead of just doing discriminative tasks. You realize that with a 2D transformer features, it's kind of the graphic the graph neural networks. You start with individual nodes actually containing spatial information, but then the whole thing gets mixed and you get lifted into a feature space. So it actually doesn't matter the order or the relative position of the token in the feature space anymore, because the way that you arrive into this feature space actually involves the relative like a spatial like arrangement between the different input like patches. So you're actually pretty good. Like you just take the features, distill it, which destroys all of the like like spatial information in some sense, but just take the features and then like feed it into downstream like large models, and it works really well.
That's
It
it.
makes you think, really. Yeah.
Gotcha. Thank you.
Thanks.
So okay, yeah, thank you.
Thanks everyone.
Because we are running out of time, so we'll move to next speaker. Thanks, Davide. And our next talk will be Spotlight Talk, which may, if I'm not wrong, it should be one of the best papers. Yeah, okay. Please. The author is Jiaxu Xing.
Okay, good morning, everyone. Welcome to my talk about we're going to present my work on attending multiple tasks for failure detection. So let me make a motivation about failure detection, why we actually need failure detection. If we look at the most deployed and most intelligent autonomous mobile robots, we actually find there are a lot of disasters. Like the Tesla autopilots, there are cases where autopilots are on, and for sure, this driver fault also didn't control this manually very well. But in the end, the autonomous cars crashed to the track. So actually, the second one is happened even in Detroit. So let me give another detailed example. Imagine you have a image, and we saw obstacle in the front on the road, but the semantic segmentation doesn't recognize the object. It will be a failure. It will be a perception failure. It will be integrated into the map. And what's worse is actually it makes the agent, make the action planning framework, make the wrong decision. And this is already very catastrophic. And what we also want to emphasize in the system is actually there is a perception failure, but the system also is very certain to the prediction. If we check the softmax entropy of the segmentation mask, we didn't see even some heat map visualized on the unseen anomaly obstacles. So actually motivated by this, what we try to do is actually given an image, give a visual task. We try to, using a proposed framework, to predict the pixel-wise failure detection results. So what we try to do, the failure detection actually indicates how much the perception results can lead to a very bad prediction. And actually motivated by the other works, there's a CVPR 18 work. Basically, they study a large number of visual tasks. They try to study the underlying transfer learning, how the different visual tasks can benefit from each other. What in the end we try to do is actually combining multiple visual tasks, try to compensate, try to explore the task consistency, and try to get a better, more grounded failure prediction results. There are actually several studies working on multitask learning, try to exploit the task consistency, but they are either using semantic to get a depth estimation, this fixed task order, otherwise they just explore the original task, rather go deep down to the failure detection mode. So much for the background. What we try to do is actually, first we have an image, we have a perception system, and what we can do, we can perform a sequence of perceptual tasks, like semantic segmentation, depth estimation, even normal prediction, and instance segmentation. What we actually want is actually the prediction failure of each individual tasks. So what do we use to bridge these two different things? There's a term actually the visual task uncertainty. That's actually the bridge we try to utilize for our task. We have an image, we have a sequence of different tasks. What we try to do is actually have attention maps where we weight individually the different uncertainty from different tasks. And we combine them, we fuse them to ending like task failure prediction. So let me give a detailed example of what's the individual components in our system. So for example, we have a ground truth segmentation mask, we have ground truth depth prediction, depth results, and also we have cross entropy in the end as the failure detection, and also the L2 norm of the depth prediction. And there are serious uncertainty. Actually, there are a lot of large community on the uncertainty estimation for the visual tasks, and we take many of them for both semantic depth and also other tasks. So let me start with our one example. Here's a clean image. We try to deploy the state-of-the-art model segmentation depths, and uncertainty looks pretty well. But the problem happens if we look at a foggy scene. This might be a huge problem for the perceptual system, where we see the segmentation basically produce a large error. This will be very bad. And we also see the cross entropy. But if we look at the state-of-the-art uncertainty estimation system, there is no actually warning of that. So actually, the uncertainty on the right part there is not visualized at all. However, what we get inspiration from is the depth estimation. There's a depth. If we check the depth prediction results, it's quite accurate. But the problem is on the road there is something wrongly predicted. Our idea is we try to fuse this thing together. And sorry. Quickly go back. Okay, I cannot. And somehow it's cautious. Okay. If we look at depth estimation, we find out the green circle is quite consistent. I mean, our idea is try to fuse the information together to make the prediction better. So that's the result. That's ours. We basically combine the depth estimation and our uncertainty prediction results are better. So more detailed, our structure, basically, we take images, we perform sequence of tasks. We have actually a large repetition study on different tasks, and that's our network. So I will show some experimental results of our framework. Basically, we choose various tasks and also different state-of-the-art uncertainty estimation method. We first evaluate our results on the cityscape dataset, including also the foggy cityscape, where there are a lot of catastrophic scenes. And what we can show is actually we use different uncertainty estimation as baseline, and we try to compare like how our framework can improve based on them. Actually, if we saw the results, like our framework basically take the uncertainty estimation from semantic and try to improve based on them. And there are some quantitative results basically show we try to use 4 different uncertainty estimation, and using the same framework, the results shows our framework can outperform the baselines. Another study we did actually interesting is which visual task do we need to get the results better. Actually, we try to using different modules, semantic only, combining semantic depths and normal. And actually quite interesting. It's like normal, in the end, we show that the semantic depths, normal and semantic depths are the best. Actually, this is explainable because the depth information and normal contains more or less very similar information, geometry information. Another experiment we did is actually we try to visualize our attention mask. Like we study the resolution, how the parameters, the resolution can help in the end our failure detection results. Not surprisingly, we find out that if we increase the attention resolution, we can have a better results. And again, we evaluate our approach on more datasets, especially Well-Dash and Dark Zurich dataset, and our results outperform the baseline by a large margin. And that's pretty much of the talk. I want to thank my co-authors, and if you have questions, I'm glad to answer them.
Yes, Sakuja, and any questions from the audience? Okay, so if there's no questions, I think this comes to the end of the first session. Next, we will have 30 minutes coffee break. So please come again, come back at 10:20. Yeah, thank you.
All right, so let's go ahead and get started, everyone. So as people are coming in, we're gonna go ahead and get started. So I just want to very quickly introduce the session chair for the second session in the morning. So Golnaz Habibi, a great friend of mine, and she's an assistant professor in the computer science department in the University of Oklahoma. And Golnaz, I hand it to you.
Thank you. Great. Good morning, everyone. Welcome to the second session of workshop today. Let me introduce our first speaker, Dr. Wolfram Burgard from Technical University of the Nuremberg. Please welcome Wolfram. Thank you.
Wonderful. Thanks for having me here. It's a great pleasure to give a talk. Although it's quite a challenge to stay within 20 minutes for a professor, but we'll see. In this talk, I'm going to present a little bit about this combination of deep learning and probabilistic approaches, which have both been particularly successful in the past, but it's kind of unclear how we can actually deal with these methods and use and combine them in a proper way. This is one of the aspects that I'm going to briefly touch, and the other one is as to whether what the role of models is going to be, like the models that we all know from in robotics and navigation, like SLAM, and also in manipulation and grasping, and as to whether there's a way to actually get rid of models, right? So this is something that I'm also briefly going to cover. So in principle, what we're interested in is building intelligent machines, right, that can perceive the environment and act autonomously. And when you map this down to a self-driving car, then you mostly come up with components like this. So this is something that you repeatedly find in software stacks, where you basically have different modules that perform the interpretation of the sensor data and mapping, localization, perform prediction, and then planning, control, and so on. And then you might now ask, what's actually in all of these boxes the best method, right? You can also think about doing all of this end-to-end, and it's just one box. But currently, this is not the predominant approach to solving or building intelligent robots. Right? So if you think about this probabilistic robotics scheme, and here the equations, and ask yourself, what is actually where do they fit best? Then that is my guess, right? You can actually make a look at where they are particularly strong. And what we all know is that SLAM, mapping and navigation, and localization, these approaches are particularly well known and super robust, and also very accurate. So when you look at, for example, localization, this is some work that we did a couple of years ago when it comes to this question, how accurate can we actually get when we perform mapping and localization. And then it turns out that even in complex setting with a sufficient amount of dynamics, which is introduced by these boxes that are added there, get accuracy in the range of millimeters. Right? So what we figured out there is that actually the localization performance is so high that you cannot actually achieve the corresponding positioning accuracy simply because the controllers don't execute your commands anymore at that granularity. Right? So this is something that where we have been particularly successful, and the same with mapping, although there's also right now approaches that can actually do this also with deep networks. But this is a particular example, and even a startup that I'm involved in, where the goal is to actually build highly accurate maps of real estate building, but also other facilities as well. And this is a particular project where we actually worked on cultural heritage and built the most accurate model of the Leaning Tower in Pisa. And we've done the very same for, I I leave it on for a second so that you can actually enjoy seeing the basement. So it's an indoor-outdoor model, right? It's not just one. So we actually take the sensors inside the building and also fly over the building and then we combine these two models, so to say, in a consistent indoor-outdoor model, which then allows people to make any analysis about these buildings and calculations about when you want to paint them, things like that. This what this is relevant for. And in a few seconds, you can fly underneath the earth and see that it's not a good idea to build something on sand. So 1 second. Could be faster, the video, but it's so nice that I actually want you to enjoy that. Right? Okay, here we go. Underneath the earth, this is the basement. Right? Okay, so this is the most accurate model also of the cathedral in Freiburg. For those who were at the RSS in 2018 or so in Freiburg, then you can actually, they might remember this church. And then these type of maps, like the geometric representations with annotations that have played an enormous role in robotics, enabled several logistics applications and also self-driving cars. Although, and this is a problem, right, like in self-driving cars in different levels, like for example for localization, but also for semantics, like intersection planning or driving through intersections, for which there typically are entire so-called map operations teams who basically build and annotate these geometric representations to make them usable for these self-driving cars. But at the same time, these maps come with challenges, right? So if you think about, the major challenge is basically that they do not capture the dynamics of the real world. And so if you think about, for example, winter time and so on and so forth, and this is not very far away, the top video is actually footage from Ryan Eustace a few years ago in Ann Arbor during winter, right? And then if you imagine that you have a car that relies on the accurate geometric representation of the lanes, then in a situation like that, you could easily imagine that this does not work anymore. Right? And you can even have very slight modifications of these maps that make vehicles fail, which is indicated in the bottom picture. It's a video from J.J. Riggs, a guy who actually frequently calls the Waymo self-driving cars and brings them into challenging situations. So it's actually worth looking into that. It shows basically the performance of these cars on one hand, but on the other hand, it also shows the limitations and the difficulties. So so that's the wrong read. So that was actually, yeah. So let's go to this other side, right? If you think about that being the strength of probabilistic approach, the question is, where is the strength of the deep learning approach? And this basically this one over here, right? So at least from my perspective, right? So we are particularly good in this interpretation part, and there's also some upcoming work in mapping and localization and so on. And prediction is also a pretty good area where these deep learning approaches have been super useful. Right? And if you look at the two together, right, then you actually might wonder, is there a way to combine them, like you see, to combine them in a proper way, because then it looks like that we can actually inherit the best of both worlds. Right? And one work that we did in my group, for example, in this context is semantic segmentation. If you take this as an example, then the key question is what basically does the world look like based on data that you have, or simply images. And so the idea there is basically to assign to every pixel or every point in the 3D world the semantics, a class, what this big pixel basically belongs to. And there are different types of tasks. The semantic segmentation is basically that assigning this to basically assigning the classes to every pixel, but then you also sometimes want to have instances. For example, when it comes to self-driving cars, you do want to know what the individual vehicles are in order to make better predictions about what the world is going to evolve, how the world is going to evolve. And that leads to the panoptic segmentation. And we also worked in this space and did some work with Kshitij. Where are you, Kshitij? It's over there. So if you have any technical questions regarding this and how to come up with an architecture like this, then ask Kshitij about these details. So with this, you can actually get super good results and get to the leaderboard of the for that problem, right? And for at least for a certain time, right? And which is good because like means that we are still making progress in this field. But the key question then is like, we have these results, like if we do get proper interpretations of the scene, how can we combine this in a probabilistic approach when it comes to, for example, localization, right? And so what we there need, right, in principle, if you think about a particle filter or Kalman filter, whatsoever, are these uncertainties, right? We need to know, like, what is the likelihood of that guess that the network comes with. And so that's not only for prediction, but also here the perception part. Right? So, okay. So this is basically the two terms that we need to know in practice. And the problem now is, and I used to call this the deadly virus for probabilistic robotics, is that with most of these deep learning approaches, we only get something like the maximum likelihood estimate about what the network guesses the world is, right, around. And then we don't have these terms anymore, right? And the problem then is that we can't do much, right? It's extremely difficult to properly incorporate this into a probabilistic framework. And I used to call this the deadly virus for probabilistic robotics, because simply like what we're doing there basically is we're having an argmax in the code. And when you look at a proper software stack for a robot or a self-driving car, then actually should in no place contain an argmax, right? So if you see an argmax in the code of your students, it's probably wrong, right? And so, I mean, in the end, like at the very, very end, when it comes to the optimal decision, there it makes sense to have an argmax, right? Because you want to have the most likely action to execute, or the most safest action, right? There it's good, but everywhere else it's wrong, right? Because basically what you're doing is you're destroying the probabilities. And some students argue that calculating on like an argmax is cheaper than doing just a sum and the uncertainties, which is not true, right? It's for both you need a for loop, right? And you have a comparison instead of an addition, right? So it's not many processor cycles that you save by doing an argmax versus like just calculating the uncertainties in a proper way. So never use argmax. And if you don't want to do this, right, if you really want to incorporate this, then the question is, how do we get calibrated uncertainties? And we need to have proper tools for making use of them. In localization, it's pretty standard, but in other places, like for example, planning, it's actually pretty difficult to properly incorporate uncertainties into your planning process. And this is where we should actually put more emphasis on, and not just, I mean, in the end, if you have perfect perception, which we will never have, then we don't need that, right? But it's actually not going to be the case that we will arrive at that stage, right? So no argmax as well. And here's one example of a way of how to potentially do this. This is a recent work that has been presented here at ICRA, also from Cioffi, about uncertainty-aware panoptic segmentation. We are basically trying to have like uncertainties together with the semantic segmentation and also the instance segmentation. And what you can see in the bottom images is basically in right the uncertainties that the network outputs here for the corresponding result that you see on the top. And which is interesting is that you see these uncertainties also, like in particular, for example, at the border between classes and at the border between instances, which is kind of like an indication that they are at least at the high uncertainty side at the right spot. Right? This is the network architecture for this. Questions go to Scherer again, right? There he is, and here are a few quantitative results in video for where you can nicely see that like between the cars, between like the road and sidewalk, there are these high uncertainties. Right? And there's another example here where you basically look at on the left-hand side, you see the error that is predicted in the prediction, and on the right-hand side, you see the corresponding uncertainties, and there is at least a correspondence between like where the network makes an error, there's also high uncertainty, which might be super useful in these applications. where the vehicle actually needs to make a decision. So that means that these type of approaches, like, and I think we are underestimating the relevance of this for practical purposes, right, are super important from my perspective. That's something that we should actually investigate more. And in particular, and this is something that we also are planning to do right now, is we're trying to figure out how to combine these approaches with a true probabilistic approach. That means that we need to have calibrated uncertainties there. Right? But at the same time, I'm also thrilled by this question as to whether we really do need HD maps. So is this really true that we need to have these representations, or is there a possibility to build robots that actually don't have these representations? Because on one hand, they're an enabler, like self-driving cars, right, are mostly based on these representations, but at the same time, they are also like a limiting factor because the dynamics of the world forces us to update these maps in a regular way, in a regular fashion. Right? Then we have been working on trying to predict what the semantics of the world, for example, when it comes to learning topology. This is a road graph prediction work that we have been that we did a few years ago, and there's a newer version that is right now it's just published. And the idea there is basically to predict the topology of the traffic scene, or of the bird's eye view that you have, or from the bird's eye view, you basically predict where the lanes are and where and how they connect. And these are some of the results of the earlier version. They never showed me examples of intersections, probably because it's too bad, but I think it's a really good starting point in looking into like this question of, like, if you think about this, that we are able to predict what the world really looks like and where how an intersection or the topology of an intersection is, then we are closer to actually building vehicles that don't need maps anymore. It's kind of like, you can build a map from one observation, then you don't need mapping anymore. You can just drive. So this is the idea. On the other hand, that's what's coming up on the horizon, is that are these large language models, which, to my understanding, like, or at least I'm like super excited about those, because whenever I talk to ChatGPT and tell ChatGPT I'm a robot and I have to do a specific task, the answer that ChatGPT gives to me is actually pretty convincing, and I always have this intuition that it can be used even by a robot. And here are a few examples. So this is a recent work that we published last year about visual language maps for robot navigation. This video is a little bit slow, but it is basically the idea that you use these large language models or visual language models to annotate objects in maps, and basically provide the robot with a deeper understanding where which objects are. And we've seen this in one of the previous talks, that by doing so, you can actually get an amazing functionality. Like, for example, like go to the keyboard, or go to the plant. That's something that the robot is going to execute in a few seconds. Or go to the chair, right? And all this without having like a single student working on a single training set, right? So this is all zero shot, so to say, and which I find pretty amazing. And one of our most recent works is also using this for SLAM, in particular data association. This is a work that was presented here as well. And the idea there is basically that we use CLIP for identifying objects, and then we ask ChatGPT, given these objects, what do you think this room type is, or the type of the room is you're in? And ChatGPT is pretty convincing in that. Right? So here I do have, like, without going into all these details, but here's a pretty interesting set of images. So if you look at the left column, which is actually my favorite, there on the top you see a kitchen, right? And in the bottom image, you see the very same kitchen from a different perspective and with different types of objects. Right? So there's actually no single pixel that is corresponding in those two images, and which makes localization and loop closure particularly hard. And so this is one of these these aspects where I think that these large language models can play an enormous role. And it's not only that you can perform localization with this, you can also ask or analyze like which objects in the scene from the vocabulary that the system uses are actually relevant for localization. And you see this here, that these living wall portraits, which are these large greenish things on the walls that they are particularly relevant. So you can first of all analyze which objects are relevant for loop closure, but in principle you can also add new words to the vocabulary and basically end up with something that I call language instructed slang. So by doing so, you basically can instruct the robot via language what to focus on. Brings me to the last thing that I want to talk about, namely object grasping. In a second, you can also do this for grasping, right? And then, so what we did here is basically we had a couple of objects, like one of these favorites is the ice cream cone there, right? And you basically tell the robot, grasp the ice cream cone, right? And then we are basically asking ChatGPT which type of the object where the robot should actually grasp. And we use clip to identify that object, and then use grasp it to sample stable grasp on the object, and then we select those that actually fall in the corresponding bounding box suggested by ChatGPT and clip. And here's a few videos where the robot actually performs grasps. On the left-hand side, you see grasp it, right? Purely geometry driven. And then we perform this. On the right-hand side, you always see the very same task executed by this system that we call LangGrasp for language model. Grasp, the system that actually is able to perform semantic grasping, so to say. It doesn't include the most favorite object here. And so there's a couple of more examples where you see more meaningful grasps executed by these robots. We also did a qualitative evaluation. We basically asked users like where they would grasp the corresponding objects. My favorite line is this one here, toilet brush. Where is it? I can't. They're here over here. Two of the users think that they would. It's completely fine to grasp a toilet brush at the wrong end of the stick. Right? I mean, what Clip doesn't know is as to whether the brush is actually used or not. Right? The one that we used for the experiment was new and never used. Right? But so okay. So brings me to the summary. And then you see that, like, with this approach, the robot grasps most likely at the places where the human would also grasp the corresponding objects, which is, and this is all zero shot. There's no learning involved. That is, directly comes out of the system. You basically plug them together, and all of a sudden it works. And if you should encounter this in your paper assignment stack for ICRA, please say yes to this paper. Okay. Which brings me to the summary. So I think that there are two things that we should focus on. One is like do invest more into this question, how to basically properly combine this super exciting deep learning stuff with these data estimation things that we have been seeing in the past. And at the same time, we also should look more into how to utilize these language models, these large language and foundation models in robotics to perform tasks that at an accuracy that we have never seen before. Thank you.
If you have any question, please ask during the break session. Thanks so much again, Dr. Wolfram Burgard. Thank you very much. Okay, let me introduce the second speaker, Dr. Lingjie Liu from University of Pennsylvania. Welcome, Dr. Liu. Thank you.
Hello, everyone. Actually, this is my first conference to a robotics conference. I'm very happy. My background is computer graphics and vision. Today I will report my research on 3D reconstruction of real-world things. For robotics, we really need to understand the 3D world, to interact with it, and also take action. Here I give some examples of the real-world things we want to reconstruct it, 3D geometry, material, and other 3D properties, and also real-world things that contain dynamics. So we also need to reconstruct the motion and the deformations from images or videos captured by our phone or the depth sensors. For this image-based 3D reconstruction has been explored for decades. So this is the setting given multi-view images, and maybe you can predict the camera parameters, and then you reconstruct the 3D. But actually, this is a widely used image-based 3D reconstruction method called CoMap. It's very powerful. It can reconstruct in the wide things, but the reconstruction quality is still limited. Recently, in 3DV, we proposed a new way to solve this problem. So we model 3D reconstruction as image rendering problems. How to do that? So we often use we use a scene representation to represent a 3D scene, and we make the render to be differentiable. And by calculating the differences between the input images and the output images, the gradient would backpropagate to this scene representation. Previously, this scene representation only used maybe one-dimensional vector to as a representation, but actually in computer graphics we have a lot of 3D modeling priors, for example, geometry, material, and physics. So we need to incorporate this 3D priors into this scene representation. One example here is a nerve. I think most of people are familiar with this work. So they instead of using a one-dimensional vector as a scene representation, they introduced this 3D structure-aware representation, radiance field, to represent the scene. But one problem for nerve, if it want to extract very high quality geometry from this scene representation, you get this noisy result. This is because the representation they used is a volume density, which lacks the surface constraints. In our work news, so we incorporate some surface constraints into this framework. So we will present the thing as a sign distance function. And then we use volume rendering to learn this representation. And in this way, we can get a very high quality geometry as shown here. And here we compare with the classical method, CoMap, and also nerves geometry. You can see our geometry has a higher quality. We also evaluate this on a diverse object. It also works quite well. This year at SIGGRAPH, we also proposed a method to not only reconstruct geometry, but their materials for these very challenging reflective objects. One problem often used and this work I just mentioned above, its training takes a long time. It often takes 8 hours to train for this specific thing. So this year at ICCV, we proposed a news tool, which can learn this thing within 2 minutes. And we can also use this for dynamic scene reconstruction. And in this way, we can get 20 seconds per frame reconstruction speed. And it's much better than the previous work. besides incorporating like surface priors into this representation, you can also incorporate some physics priors into this problem to synthesize, to reconstruct like a physically plausible without. So here I show example. We add like a differentiable physics component into this pipeline, and in this way we can learn this smoke in a physically plausible manner. For humans, actually, for human, we have a very good parametric model. For this simple model is a multi-person linear model. And we can use these multi-person models for as like priors for learning this representation for humans. And after we learn this animatable human representation, we can drive this to move and show. Here we show our results. If you know like the camera trajectory, you can also make use of the camera trajectory to make this radiance field more compact. So here we show example. It's quite useful for the cases in autonomous driving because you can like reconstruct this scene with free camera trajectory. But normally in the real world, we may not have like multi-view images. What we often have is a single view image. How to still like reconstruct this high quality geometry and 3D properties. So this is a problem from 3D reconstruction to 3D generation problem. And to solve this problem, we need like some generative models as a prior because we need to handle the uncertainty in this learning problem. At ICML this year, we proposed a nerve diff. What we want to solve here is that given like a single image of an object, you reconstruct it's 3D. The main problem here is that there are many probabilities for occluded visions. For example, different appearance, different geometry, and how to model this uncertainty. So here we use the 2D diffusion model to model this uncertainty. How we do this? So this our method consists of two components. One component is an image condition nerve. It's a given like a single view image, and then you predict like infer what the 3D representation looks like. But this step doesn't consider any uncertainty issue. So if you see like the output of this pixel nerve, you can see the result is quite blurry. And then we add like the diffusion model after with the conditioning on this pixel nerve's output. And in this way, we can get a very sharp image because for the diffusion model, they found like the path in the distribution to get a very sharp result. But the main problem here is that you cannot get a multi-view consistent result because for different views, you don't have like a 3D regularization on different view generation. And then for different views, they would select different parts in the diffusion model distribution. And in this way, it's not multi-view consistent. So we proposed this nerve-guided distillation. After we train this model, we distill like this 2D diffusion priors into this 3D representation. So we alternate into two steps. We first synthesize novel views using this pipeline, and after that, we fine-tuning these nerve models with the diffusion output, and we alternate these two steps in the denoising step, and to get both like 3D consistent and sharp result. Here we show our result. So compare with like previous work which didn't have any components to handling uncertainty, you can see like some blurriness on the occluded region. And if you just use the output from the diffusion model, it's not multi-view consistent. Sorry. We also tested this on the wheel data, and it works well. And recently, we also proposed this method. So we use instead of train this diffusion model from scratch, we used like a pre-trained 2D diffusion model with a trained observers, which is a very large data set, and for this single view reconstruction problem. One problem of this using 2D diffusion model for 3D reconstruction, the main problem here is it's quite slow. So for this fine-tuning stage, it often takes 10 to 15 minutes. So how to make it more efficient? At SCCV, we proposed this method called single-stage diffusion nerve. And our key idea is we want to add like this noise directly on this 3D space instead of like using fine-tuning to distill like this 2D diffusion priors into 3D. And in this way, you can do like the denoising step in the 3D space. But the previous work, actually, they have like 2 stages, because if you want to do the denoising in the 3D space, you need to have like the 3D ground truth. For example, here we use a triplane representation. So they have like 2 stages. One is that you use a nerve to reconstruct for each object. You get this ground truth triplane representation, and then you train like a 3D diffusion model for denoising. The problem is that if you have like a lot of views, for example, 50 views, that's okay. But if in your training data you only have 3 views, this result is not good. Even that you used a very strong regularizer here, the result is still low quality. In this work, we propose a single-stage diffusion nerve, which means that we train like these 2 components together. We get using diffusion model, we get like the 3D representation, and we use a nerve, and then in this way we can use like this 3D diffusion prior as a regularizer to regularize our learned 3D representation. And in this way, like we can train like on 3 views and have a very like efficient 3D reconstruction results. So what's next? I think for next step is to model more complex things, because in the real world, the things is more complex than currently the data set we are working on. For example, here like we have like human and object interaction. So if we can understand these complex things, we can take action like in this real world things. And another problem is efficiency, because I know in robotics you want to have like this real time performance, but our current method is still like there is a gap. Finally, I would just thank all my co-authors. If you want to know more work about like in my group, please check my website. Thank you very much.
So much, Dr. Liu. So I think we have a few minutes left for other questions, if you have any question.
Yeah.
The work you're doing in scientists about
yes.
incorporate models where you brought in primitive shapes to reconstruct. The paper was all learned primitive features for the SDS.
So this we learned this at SDF. We didn't like do like different components for the object thing. We just learn as like a global SDF representation. Thank you.
Can there be one more question?
So for a lot of the nice reconstruction work, it's not real time. Right? What is the fundamental gap, or what would it take to get there? What are new algorithms, or is it a question?
I think currently it's still training takes the time. Because for example, you training a neural network, you cannot assume like it can do this like real time. But that is why I think we need to have like this generalized method. As I show in the second part, maybe in this way we can have like a zero shot learning at inference time. But if you want to do like as a reconstruction problem, then it takes the time to learn from scratch.
Okay, great, thank you so much. I'm introducing the third speaker of this session, Dr. Christoffer Heckman, assistant professor from University of Colorado Boulder. Welcome to the board. Thank you.
Thank you. All right, so today I'm going to talk about two different tales that I have from the Subterranean Challenge and different work that we've taken from that. And Kostas really teed this up well from this morning's discussion. Just in case you weren't there, here are some photos from the finals course at the Subterranean Challenge about a year and a half ago. And what this looked like was essentially, I guess it was 2 years ago now, wow. Essentially large caverns combined with small little corridors, low illumination, and other types of visual obscurance. In the end, we did fairly well. Our team placed third. We used a combination of Spot and Husky vehicles. And I'll talk about our sensor stack in just a bit, but I wanted to give a little bit of an idea of what happened afterwards. So many teams did quite well. I think we should all be proud of ourselves. We did something that I think was at the start of the competition probably not expected to be done so well. And so there was a little round table that was basically discussing, is this a solved problem, or what components of the Subterranean Challenge, that is multi-robot exploration in underground environments that are visually degraded, have been solved. And some people said this is a solved problem. I thought that was quite interesting because if you look at the scores, obviously, these are pretty high scores, but they were out of 40. Which means that for the most part, the teams that did pretty well only found half the survivors or only found half of the objects of interest in the scene. And so it's clearly there's some places that we can go forward, right? And when we look at where there were gaps, I'm going to talk about two different areas today, but I think there are many, so I'm not going to talk about all of them, and we can have a discussion afterwards about that. Task one was metric localization. Clearly, we needed to be able to localize ourselves in the environment in order to find artifacts that were interesting to DARPA or survivors, simulated survivors in these scenes. And they had to be found up to, I think, 5 meters accuracy after traveling about 1 kilometer underground. So, in GPS-denied environments, that relates to something like 0.5% drift. And so this is kind of like a little sketch of what that was looking like, where you had to go into these caverns and then precisely pinpoint where these objects of interest were. The second is related to human interactive autonomy. And this isn't exactly a perception problem, although I will frame it as one during the conversation today. There are certainly different aspects of this research problem that could be studied from different angles, but I do want to give some context that I believe could be helpful in solving this issue. And in the cartoon here, this tale will be go down the hallway until you find a backpack and then turn left. And so in this sense, I'm going to kind of build a little bit on what Wolfram was talking about just a few talks ago. So let's focus first on metric localization. And I want to give you an idea of how challenging these environments are. So this is just one treatment of different illumination in one particular cavern. This cavern's in Colorado. It actually is the Gold King mine, if any of you remember that one. That was the one that had the huge disaster of spilling a bunch of mining fluids and then ended up poisoning the Atanasov River and causing an enormous fish kill. That was just one illumination treatment. In the next scene, I'll show you another illumination treatment. Same scene, different illumination. This one was slightly more diffused. What you'll notice is that onboard illumination generally causes some pretty different types of visual feedback in the environment. And then finally, this is one in which we tried to apply a slightly different type of treatment, one sort of more telescopic illumination and then one broader one. And you can see here that there's some pretty heavy motion aliasing between the illumination playing on the geometry that gives rise to quite a different appearance in the scene. what does this mean for metric localization using cameras was the question that we wanted to ask. So we started doing an initial investigation of this problem by first, as one does in all robotics problems, collecting a data set, because going into these mines is very challenging, so we need to be able to run different types of algorithms and then sort of deploy them and see how they resolve. So this is just a few different scenes from the onboard illumination visual inertial odometry dataset, or OIVIO as we called it. And what you'll see is that if you were to look at some screen grabs from this dataset, that there's 4 different types of visual challenges that we saw. First, illumination drop-off in these narrow corridors. Second, bad exposure as a result of different types of settings that were set on the camera. Motion blur as a result of how we're moving, and then specular highlighting, that is very reflective objects, like that little piece of paper that is laminated in the middle of the bottom right image, reflecting in a way that would not normally be what you'd see in this scene. And so these 4 different types of problems are just a few snapshots of what we saw when we were collecting this data set. The data set was taken by providing some ground truth in the form of loop closures, as well as, in some cases, using a robotic total station. So here are some other snapshots from that. And I want to show you some results about how our visual SLAM techniques of the day sort of handle this problem. But I want to also say that, you know, this is October, and I believe that we created the world's spookiest data set, if that ever was an award. So here's what these scenes look like, okay? So what we have here is, on the left, an OKViz, or a visual inertial front end. In the middle, OrbSLAM, which is essentially a visual-only indirect feature-based method. And on the right is OrbSLAM only using mono, a single camera, versus stereo in the middle. And this is the number of frames in which there were errors that made one lose tracking. And so you can see even in the OKViz situation in which you're using an IMU, there are some frames that you lose tracking on. Quite interestingly, though, what you'll notice is that we did apply different light treatments in the scene, and then that did not really directly scale in the way we expected with how the different methods performed. So for instance, at low illumination, like the 15% light treatment, as you'll see, there were many scenes in which there were loss of visual tracking. And yet, when we applied greater illumination, that didn't necessarily result in better tracking. So the 50% illumination in the OrbSLAM stereo system actually did better than in the 100% or max lighting that we could apply. This gives rise to this question of what kind of illumination will you actually want to use, and what does it get us to be able to model different types of illumination potentially. So just bearing down a little bit more on that question, here's some figures that we created to show how did OrbSLAM, OKViz, and direct sparse odometry, or DSO, do in this scene. What you'll see is that so the sooner you get to 100% or 300 number of runs, the better, right? That's the number of runs in which you got small amounts of pixel alignment error. And what you'll see is that in OKViz stereo, that's sort of the best one, although pixel alignment error of two pixels is still pretty bad. But the ones that don't use an IMU and the ones that don't have stereo methods are the ones that generally underperform. In particular, direct sparse odometry does quite poorly. And the reason for this, as we hypothesize at least, is that there's a significant reliance on the brightness constancy assumption in the scene for DSO, an issue that we could potentially resolve by modeling illumination. Here's another figure of sort of what happens when you go through these different trajectories and apply different visual state estimators. What you'll see here is that there's a loss of scale precision, or a drift in scale that is being estimated in the DSO cases in the bottom two. So what does this mean for us? Well, we were interested in what it means for what if we bring this light source with us. So let's take a step back and really think about what is an image. It's essentially, and I'm sort of simplifying this just a tiny bit, geometry, lighting, albedos, and reflectance. And geometry includes some of this conditioning information in it. and the lighting is sort of a treatment that you would apply. And normally what you would see is sort of like in this cave simulator here, an RGB image and some depth that, let's say these are our two inputs, and we're trying to reconstruct the image, okay? So if you decide to do sort of a standard approach in which lighting is constant, like what is generally assumed in many of these direct methods, then you're measuring an image, you're estimating some geometry based on a depth channel, and then you're also going to do some combination of albedos and reflectance into color. And the result, if you decide that lighting is constant, the left is the ground truth reconstruction, and the right is using a type of infinitam approach using this direct method for alignment, these geometric kind of artifacts that are generated as a result of just the system trying to catch up with itself and illumination being in a different place than expected. So those ripples you see on the bottom are places where the geometry has to sort of be corrected as you were taking more data. So we decided to extend this a little bit and ask the question, well, what if we break this problem up into smaller pieces? We're going to measure the image as always, and we're going to estimate the geometry using an infinitam type of approach. And we're going to estimate albedos and assume constant reflectance, something like a BRDF or reflectance distribution function that is sort of uniform, not necessarily specular or Lambertian. And we're going to model lighting. This is the real key to this, though, is putting a light source right on top and then walking it through the scene. And what you'll see is that our method is able to do reconstruction. Don't mind those little black artifacts as a result of some bugs in our CUDA code. But the reconstruction is slightly better. And just in case you're actually wondering, is this better? Well, on the right, I can plot some errors. So sort of the brighter colors are errors in the reconstruction. And you can see those propagating errors as a result of the top method that apply the brightness constancy assumption versus the modeled light source that we have in the bottom, and the 3D reconstructions are significantly better, at least in that case. And so those are some ideas of how this problem actually had to be driven all the way home in order for us to sort of think about what if we were working in a low illumination environment, had to bring a light source with us, and apply visual types of methods. And like I mentioned, though, that was only part of what was going on at the Subterranean Challenge. So they also were willing to throw in some visual obscurance like fog, and some dust and other things. So, I mean, what if we could just, avoid our the use of visual methods altogether? And that's what gave rise to some of our millimeter wave radar research. If I couldn't get this video to work, there it is. So, not going to dive into this here, but millimeter wave is something we focused a lot on in recent years. We collected a data set in these types of subterranean environments. We've been building some algorithms that can be fused with other ones, like other techniques like inertial and LiDAR-based techniques to be able to get us localization mapping. But in the end, let me just give you the punchline. We decided not to use vision in the Subterranean Challenge because some of these problems for metric localization in vision in these types of environments, I think, are still decidedly unsolved. So let me look at task 2, and this is sort of the second tale of today, and then I'll wrap up. And this is, what if we were, as in the Subterranean Challenge, interested in having a human provide their input into the autonomous system? So here's what the Subterranean Challenge human supervisor interface sort of looked like. A single human was able to interact with a system that was fielded inside of mine. And what you'll see here is there's a number of different interfaces that this individual human supervisor has to sort of attend to and provide different kinds of input and guidance toward. And if we were to do a little bit of forensics on what this human supervisor was focusing on during the competition, what you'll see is this kind of plot. This is something that is actually a little trick that we focused on quite a bit when I was working with Amazon for a short period of time on their Scout project, which is related to when is the human having to be engaged with the robot in order to take over from the autonomy stack. And what you'll see here is the green bars are places where either the human on the bottom row or one of the 4 robots in the top 4 rows were doing nothing, essentially. They were just kind of on autopilot. The robots are using their autonomy. And the orange is when the robot has to be intervened upon by the human. And then you have that human supervisor in the bottom bar, and that human supervisor sort of working on, in his case, whatever he had to do in order to fix the robot autonomy stack from going haywire. And for those in the know, our percentage in green was 52% for the full system, and our mean time in green for the full system of robots was 3.5 minutes. That's pretty good. At no time was there a race condition between the robots and the human supervisor's attention, which was also good because that would lead to catastrophe. That came to about 9 minutes of mean time in green per robot, which is actually pretty remarkable. So in the end, this is what we were able to explore. Not much, but enough to score enough points, which was pretty nice. So the human supervisor actually had to click on different things, redirect the robots to do whatever they were doing at those times. Even at some points, taking over the joystick, like we had an Xbox controller, and the human had to give direct feedback or direct commands. And so we had started wondering, well, what if we wanted to add another robot? It turns out that 4 was pretty much the optimal for what we could do. We'd done a bunch of testing with our human-robot team, and we could only add 4 robots and 1 human. Obviously, a 5th robot would have done quite well. If we could add 6, 7, 8, that'd be great. But the amount of time it took for the human to intervene on the robot was just too great. So we started asking questions like, what does it mean to improve this? So what we would have liked to do is be able to give feedback or commands like this. Go to the blue bin on the left of the red backpack, which would have required doing an object detection on the blue bin and the red backpack. And so this is actually pretty challenging because of things like this, where there are these kind of pathological examples where if there was some kind of less well-defined instruction, go to the chair on your left, this chair works and that chair works. So yeah, there are some ambiguities related to these instructions potentially, but that just means that we need to be able to use some sort of context. And of course, in the new world of large foundation models, we started wondering, what can we use these for? So this was one solution that we've recently developed in order to address this, where we use a lot of standard robotics techniques, including the building of volumetric maps like octomaps and visual inputs. And now we add, as an addition, a navigation command, which is something like go to something that is useful for something else, or go to this thing that's next to this one thing. And so in this case, there's a query that says go to the person who's sitting down, and we can go ahead and create a code generation block when we feed in a navigational API that's available to the robot that is able to consume visual inputs as well as this navigational command, and then result in some sort of conditioned layer of code that is operating on the vision input, runs a object detector, in this case GLIP, and then outputs a waypoint. And so from there, you can actually pretty much do whatever you want, like a path planner, like a normal old RRT path planner. And just bearing down a little bit more, since I only have a minute left, the code that's generated from the large language model in this case is actually pretty readable. So here's sort of what this execute nav command code would look like as a result of the find a tree and find a person sitting next to it. And here it says detected trees, and go ahead, if there's a detected tree, sort it by which one's maybe closest to the center, and then figure out where it is, choose the middle tree from that list. Go to the middle tree is actually the command here, and this is the code that was generated from the large language model. Oh, sorry, that didn't show up, but here it is. So find the one that's sort of in the middle, if you will. And so we're really interested in these types of contextual perception examples, like go to somewhere where I can watch a movie, and then here's the 3 images that are shown from the spot robot. And in this case, what we can even see is that there's this TV that is viewed, but it doesn't really mean that you can watch something there unless there's a chair or a couch nearby. And so what you see is that actually this code, go to somewhere where I can watch a movie, does in fact look for a TV and then a nearby chair, which is pretty remarkable. And this is, again, in Wolfram's words, just entirely zero shot. We didn't do any learning here. So this is just one quick example where the robot then can execute the command to go to the chair that's nearby the TV that you could go watch a movie on. And the one closing comment I'll make is that our results were pretty good in code generation. That is, if this code were to be able to find all the rest of the objects from some oracle, we'd be able to execute the rest of this pipeline correctly under that condition. But the leaky part of the pipeline was in fact object detection, which surprised me a little bit, because we've been, regaled with great object detectors over the past 10 years, and it comes back to that we still can't find objects sometimes, so our solution is still not exactly correct, and that's using a GLIP object detector. And with that, I think I'll close. Thank you for listening, and thank you for the organizers for putting this together. I have 2 minutes if there are any questions.
It looks like monocular sounds a bit challenging, right? And I wanted to see what's your take on is it like a saturated tool that feel like we can't make any problems, or are there open problems there that we work on?
Yeah, so generally I would say the open problems here are related to the challenging cases. Visual SLAM in indoor environments in sort of indoor and well-behaved environments. I think we have many great solutions there, and there are still great solutions being developed today. The question really has come down to which applications we're applying these in, and we've also, these subterranean environments are not the only ones in which active illumination is applied. So there are a bunch of areas where, even in self-driving cars, if one were to move away from LiDAR, then state estimates wouldn't be great. Now, of course, in self-driving car world, like HD maps are the way to go, essentially, doing relocalization rather than SLAM. So in applications where SLAM is required and visual with an onboard light source, as an example, are being applied, I think there's a lot of lack of research there. But it's not just that. I mean, I think that there's many other cases in which we have convinced ourselves that the visual SLAM problem is solved, but there's still some challenges out there like multi-weather. But there are good people working on all those problems too.
Take one more question.
Yeah.
Tell me more of your experiences using radar with the subject.
Yes, I would love to. So the question was about radar. So radar is a sensor. There are a couple different radar sensors out there. One of them is a 360-degree Navtec type of radar, kind of like a pencil beam 2D radar. The other one's a 3D radar, imaging 3D radars. Those are the two classes that I would generally categorize them into. And 2D scanning radars are actually remarkably good. There are many researchers, Paul Newman, Tim Barfoot, and others who have done great work in looking at how one can do state estimation using those radars. In 3D radars, the problem is that they tend to be sparse, so that these little points that you get back from them are pretty noisy. And as a result of multipath can be, they can kind of just show up and then go away. And so what I think there's an open research question on is how to use the sort of denser radar outputs. And I'm very interested in that. So, but the last thing I'll add is that the Doppler channel you get from radar is quite useful. And so as a result, if you have a MIMO type of FMCW radar, you can really get information that these other modalities at this point don't really get you. Thanks for the question. I think that's out of time. Thank you again.
Okay, now we are moving to panel discussion, the first panel discussion today, which is chaired by Dr. Nikolay Atanasov from UC San Diego. He's assistant professor in UC San Diego. Please welcome Dr. Atanasov to the stage. Thank you.
All right. Well, hi everyone. We have in my opinion, a very exciting part of the workshop next. We're going to have 5 panelists in this part, and the idea is to engage the audience as much as possible. I have some questions prepared to get things started, but I'm going to invite you all to please start a discussion. In my opinion, that's the point of a workshop, is where we get to challenge each other and discuss what are the big open problems. You can always ask a question by just going up to the mic or raising a hand, but if you're shy, you can also submit a question online, and we can monitor those and ask it for you. So I would like to invite our panelists on the stage. I'm going to do a very brief introduction for each of them. So our first panelist is Professor Wolfram Burgard. You heard from him not long ago, but I'll do a quick introduction. He's a professor at University of Freiburg, and I think we all know him well, but I still have to say some important things. So he's one of the authors of the probabilistic robotics book that we have all looked at very carefully. He has many fundamental contributions in SLAM, including Octomap, RGBD datasets, G2O, and if you look at his Google Scholar page, he already has a paper from 2030. All right, our next panelist is Professor Ayoung Kim. She is at the Seoul National University. She works in SLAM, underwater robotics, and place recognition. Our third panelist is Professor Davide Scaramuzza. Davide is at the University of Zurich. He's done a lot of exciting work in UAVs and quadrotors. He has a work on champion level racing for UAVs, event-based cameras, VIO, learning to fly, reinforcement learning for flight. Is Davide around? I saw him this morning, so maybe he's just a bit late. We'll wait for him. Okay, then moving on. Our fourth panelist is Professor Sebastian Scherer at CMU. He's worked at the DARPA Sub-T. His team had a very impressive performance as well. His lab has produced the Tartan Air dataset, as well as a lot of work on off-road driving, UAV navigation. CubeSlam is another paper that stands out. And then finally, Professor Teresa Vidal-Calleja from the Robotics Institute at University of Technology, Sydney. Professor Vidal-Calleja is working on robot perception, sensor fusion, sign distance functions, and Gaussian process techniques. And she had a really exciting keynote yesterday, so I'm sure you've seen some of her work. All right, so I think let's get started because we have some time, but not too much. So to kick things off, I have a few questions, and I think maybe the most burning one that I'm sure lots of people are talking and thinking about is what's the role of foundation models? We'll be hearing so much about them. So specifically, where do we see foundation models making an impact in robot perception and SLAM? And sorry, we do have microphones.
Okay, well, we saw it in a couple of talks today. I think the interaction with humans is where there is the key driver to combine these large foundation models with robotics. And you can already two of our speakers mentioned that it's just zero shot. You can just use them as it is, and they actually work, as opposed to other methods.
I guess, I mean, they do form a useful feature space to do things, and one of the things that will be interesting to see is if you go to environments that they haven't seen as much in sub-T like spaces, and we saw some evidence, but I think it will be interesting when you get to the edges of the data sets. I will generalize.
I mean, for me, it's not just limited to human-robot interaction, because they also can do some sort of planning, at least for shorter term plans, I see like 7, 8, 9-ish steps are pretty good when you ask ChatGPT. But if you think about like maze-like environments, or I do not know how good it is at Towers of Hanoi, never tried that. But so really where you think these good old logic style planning with these logic puzzles, I mean, it has been pretty bad. I do not know where version 4 now is, but it might be better and better as time goes by. Right? So I think it's pretty open-ended, and so right now I'm pretty convinced that we can achieve a lot more than we have been achieving thus far. I doubt that you can take them in underwater or in caves that we have seen, right? So it's probably not that easy, but maybe some subtasks there can also be solved using the existing models. The limitation is that we are right now stuck with vision language models or vision or language models, and we don't really have a real robotics model. So that's so basically where we can output controls based on that what we see, and then that might change the game, but it's obviously going to be extremely hard to accomplish. So I think we are having great opportunity right now to look into these things and show robots that have better performance in various types or various tasks. But at the same time, I also see some limitations, like special fine tuning also is also open.
Right. I want to catching up from Wolfram's word. I think we can maybe use the language model for underwater and caves. I think we've seen many HRI interaction, and the SLAM can leverage the language model or the foundation model. But also in the small task, for example, some of the things that we are all doing for the visual localizations, we like long time ago we have been using visual words, but something that I found out is the language model or the visual sentence translation can help. So I think like sub-module wise, there's a many possibilities that we can incorporate the language model or the foundation model, not only to mention the HRI or the past plan.
Davide, come up here.
Hi, Davide. Okay, let's keep going on this theme. So one thing that should strike us immediately is that these models have been getting larger and larger, and they supposedly take longer and longer to train and require a lot of data. So when we start thinking about autonomous robots, I think some kind of important questions are, what should be learned offline and what can we optimize online? For example, in SLAM, traditionally, we've always done a lot of optimization on board the robot, while now we are in this regime where we do a lot of learning offline. So what's the right trade-off? And a related question is, do we see limitations for deploying such robots such models on robots in terms of memory or computation? Are we going to have robots that are always connected to the cloud, or should we still have robots that have the model on board? Davide, would you like to take the first question?
Yes, just a disclaimer. I have to give a talk in my workshop in 20 minutes, so I will have to leave. So, yes. So we are working at the moment on fast-flying drones. So to answer your very last question about how much can we actually learn online, of course, the problem is that when we refine a policy with reinforcement learning online with such a safety critical system as a fast-flying drone, this becomes a problem. At the moment, we focused on, for the past 2-3 years on learning offline in simulation and then fine-tuning with the data collected in the real world, but the real world data is only used for improving the simulator and then fine-tuning in this augmented simulator. But we're also looking at strategies indeed to fine-tune in the real world. Regarding your question about what should we learn in the real world, maybe, for example, deviations from the simulated models, this could actually be done online, so things that do not affect too much the safety of the system, so like calibration parameters, model mismatches, also, for example, aerodynamic effects, and so on. That's the things that we are actually looking at.
I would like to build up on the point of Ayoung. I think something that we definitely can build offline and have like bag of words methods in the past. I mean, we've proven that have worked very well. So learning heaps of features that and learning the connection between those features that can be online. And with the new large foundation models, exploiting that type of approach, that would be something that is definitely a path forward, because those type of features are small enough that we can load them on the robots for deployment later. So I guess those kind of models will be useful.
Yeah, I mean, I think there's some inherent time scale to the tasks. Like some, let's say, control. There's no choice but running it on the robot. Some things higher level can be offline, and so I think we'll see this kind of hybrid paradigm where some things do on the cloud, some things you run on the robot. I mean, some of these foundation models you can run on the robots in small compute.
I have not much to add, so I think one of the key questions is also when it comes to these large training or these large models is like how we can actually also adapt to a specific situation. And even if you think about, we're somewhat stuck with these models as once we use them, right? We cannot really optimize them and adapt them to the situation. So like if your robot performs suboptimally using such a model, then will always perform suboptimally. And like we currently do not have a methodology to, on top of them, perform some optimization or learning. So that's from my perspective a real issue, and we also cannot train them because they're simply too big. Right? I mean, some of them you can download, and I haven't done any experimentation with, or we haven't done any experimentation about, or you can actually, whether you can actually adjust them to a specific situation. Yeah, so I think this is somehow the downside of this, and then it's also the question of how to continue from there.
Yeah, I totally agree. I think it depends on the application that we are shooting for. So, like for example, like David's work is the drone racing. There's no way that you can wait. But some of the project that I'm working on, the construction site monitoring robot, is okay to have just rough estimation of itself. And when it comes back, like over an hour of time, if we can accurately detect what's the difference and and then that time the robot can synthesize view and spare some time. So I think it fully depends on the application.
Maybe just one comment. I think we're also going to see that move from large language models to smaller models that have more reasoning and so can do the same thing, right? I think right now we're kind of in this balloon stage, and I think things are going to collapse. We might have some more symbolic reasoning in these systems, and it's going to get a little smaller and more reasonable.
We have a lot of questions online already, so Kaveh is going to ask some of the exciting ones.
Yes, we have a lot of great questions online, so I'm going to try to ask them. By the way, if you scan this QR code there, it should take you to the online portal where you can type your question. But I also want to encourage people to raise their hand, and I'll bring the wireless microphone to you. I think that's more interactive, so you can ask your question directly. Also, feel free to walk to this microphone here and become public format line here and start asking questions. In the online portal, there's also a mechanism for you to upvote or downvote questions, right? So I'm going to start with the one that has the most votes right now, which is, can foundational models in Islam really overtake geometry-based Islam, given the vast amount of data that would be required for training and generalization?
I think it shouldn't be taking over. I think it would. But I always advocate for using a mixed model, like where we exploit geometry and the traditional methods. and combine them with potentially large language models or other type of learning algorithms. I think that getting the best of both worlds is it's the way to go. I wouldn't go all just language model learning, but that's my view.
So I think the jury is out on this, on the answer. So I think I'm gonna stay neutral in this because we pursue both ideas, and I think that.
I mean, never say no, right? So it might be the case that, there might be examples where these language models are actually better than the traditional approaches that we're having. Like, think about this one example that I showed where you can actually also like tell the robot which objects to focus on in a particular SLAM task, right? So, I mean, we also saw this, that when you go in caves and all of a sudden, like, these standard methods, like, are not that performant anymore. And there are two ways dealing with this. One is having your PhD students work on that for a long, long time, right? The alternative is try out a foundation model that maybe like allows you to like do better loop closures or so, right? Or I mean, I currently don't have an idea how to do like visual tracking with foundation models, but it might even be that even in a tracking task, you could use a model like this in order to focus on specific features that are better for tracking, or excluding certain features, right? If there's a dynamic object, right, and that runs through the scene, then you could tell the system, hey, don't use the car for tracking, right? So there's all kinds of applications that you might think of that where tasks that are where we think this has been done like with the standard feature-based approach, and a lot of programming can be supported substantially by these foundation models, right? Which I find pretty amazing.
I wanted to say one more thing briefly. I think as a SLAM person, I think we SLAM people have been fusing many different sensors like LiDAR camera. I think language model could be one nice sensor modality. I think.
Okay, so I want to say that if is this on or not? I don't think so. If anyone has a question, please raise your hand and we'll bring a wireless microphone to you. So I just want to give you a couple of seconds to see if anyone wants to ask questions directly. Here we go. We have.
Thanks for the wonderful presentations today. I come from an industry, and most of the challenge is what you showed here is having a big model, having multi-model like you have vision, lidar, and radar sensors in automated vehicles, fusing together, and also in addition to that, you should think about situation analysis when you drive. So, what is your thought, and what is the path which we see forward when we put those big models into a small embedded chip, fusing them, and also understanding the situation? So, what's the best approach? That's one question. Second question to Professor here who introduced the probability. We also saw the probabilistic model has a possibility to reduce this model because we can understand how certain layers are more important when compared to others. We can prune them or we can improve them. What are the current research in this field?
Yeah, I didn't get your question, the second part of the question exactly, but so maybe you can, if you can rephrase it, then.
Yes. In some of the papers in probabilistic approach, we can understand that each layer's probability can be estimated. From this, we can prune or we can reduce this size by pruning this, depending on the variance, so that the size can be reduced. Some of the papers talks about this. So do you see this going forward a good approach to reduce such big model size?
I don't know. Okay. I can't tell you, unfortunately. So, I mean, so it would be like, I mean, I think it's important to look into this, and there's definitely also a challenge, like how we can reduce these models or can use smaller models for doing the very same tasks that we need, right? So, but I mean, definitely the more parameters you have, right, the better you can perform your pruning, right? And you would actually, right, there are some ideas on how to do this, like focusing on areas where you have high uncertainty, right, where you would basically use, like, do training in these spaces as well, right? So, but this entire question how to actually get training data from from your probabilistic estimates is also a pretty open question, right? This goes into this active learning space and so on, where you would actually try to figure out, try to ask, like, what is a situation that will help me reducing my uncertainty, or what is an example that will help reducing my uncertainty in a particular task that you're having, right? And these are open questions, right? And maybe you could even ask a foundation model for doing this, right? But I don't know.
Yeah, we'll take one more question from the audience.
Yeah. So I was wondering, from the robotic literature, we have many, let's say, requirements or fundamental concept that we like to maintain, like, for example, uncertainty estimation, like some guarantees and control. So like, there are so many things. So what are, in your opinions, some of these concepts that we should take that are required to advance and use these large language models? Something that we should really not miss, and that the whole community, not only robotics but also deep learning, should consider while developing these new kind of models and new techniques.
I'm gonna start. Yeah, I think that's I think a spot on question. There are many things that we learn over or have been developed over the years. Like, for instance, kinematic models of a manipulator, right? We don't need to learn about kinematics. That works. We should just use it in combination, for sure, with other with learning methods. But it's given, right? And of course, you can learn deviation from this kinematic model, but that makes it simpler for learning, right? We know those models, if they work. For instance, in estimation, we have, we use uncertainty to do data fusion, and that, I mean, if the assumptions of the noise models are okay, it's a very powerful tool that we could continue using. Potentially learning how to fuse with different type of noise assumptions. Well, that will be interesting. But I mean, the fusion methods are pretty established, so we can potentially use them. And well, I don't know, other types of models that we know that they model well the world. I don't know, like sensor models, like range and bearing for a LiDAR. We don't need to learn it; it's given. You know?
If I can maybe add.
If I can maybe add something to my question, like if you could choose something, like some of these fundamental things that these large language models or some these foundational models could respect, what would you choose? Like if you have to choose, like, let's say two, like, okay, I would like that my foundational model would respect my control constraints or something like that. So maybe like something very specific that you consider fundamental for advancing in robotics with deep learning.
Yeah, I think for me it's an easy question. You have Jessonorin, you have to make it work with the Jessonorin. You have to get rid of the many heavy parts. If you have a GPU equipped server on your side, then you can use whatever you want, and why go for it?
To be honest, that's but this is my philosophy, right? Everything can be questioned, right? And for me, nothing is cast in stone. And I mean, it's completely viable to actually ask: do we actually need to have a kinematic model, right? So I used to say, like, so since when do we know mechanics? right? Few hundred years, something like that, right? And still, people were able to successfully kill animals by throwing spears at them, right? So, so they didn't even have the equation, right? Nothing was known about gravity vectors and things like that, right? So, I mean, and I think the math is nice. I like these equations, right? Now, don't get me wrong, but I don't think that we should actually say, but we need this and we are not going to question all of that, right? So for me, it is an important fundamental question. Like, can we do things even without models, right? For me, this is a definitely viable question, right? So can we operate a robot without a kinematics model, right? So can we learn this on the fly, even when the robot grows? I mean, these are all things that are of fundamental nature because we grow when we also our kinematics model changes, right? And we do not have exact odometry. So and therefore, I think for me, it's completely fine to question all of this and to ask, like, is there a way to achieve potentially the very same performance without putting these equations down? And I know that some people don't like this. There's this ongoing, lifelong debate between Osawa and me about this, but this is how it is. That's my opinion. You asked me.
Yeah. Maybe just one follow-up. I think right now we're in this kind of feasibility stage, right? Like, people excited about, first model and so on. But then I think where robotics can come in, different from machine learning, is right. We have all this existing work of actually making things work for real and guarantees and so on, and like essentially answering that question, right? We have these tools, or do we only have X and Z, or Y and Z, or whatever, X and Y? And so, so I think that's. But then I think I'm maybe more on the model side. I think there's, I mean, I think there's a lot we can learn from a model, and I think that a model is an abstraction that's very powerful when you have it, right? So I think. Doesn't mean that it only has to have a few parameters, but I think models are nice. Anyway. And then there's a safety question, what do pass the feasibility?
I agree with everything that has been said so far. I believe that in the future we will have two layers, a cognitive layer and a computational layer. I mean, now think of ChatGPT. At the moment, it cannot solve multiplications between two numbers with more than 4 digits. So if you can interface it with a calculator, then you will be able to do it. So in the future, we will have basically systems that reason like that. So I think this is going to be what we're going to use it. But I mean, also what Wolfram said before, I mean, that you can learn everything is also possible. I mean, now they're using also the methods to make scientific discoveries and also, predicting new laws of physics and so on. So I don't know, everything is possible.
Since all of our panelists are from academia, I have one question related to graduate and undergraduate education, again related to foundational models. So going back to the part that these models are starting to get very large and hard to train, I'm wondering how do we see them being, what's the role of academia going to be? Are we going to have the resources to use those models and train them? And specifically for graduate students who are starting their PhD, what are some of the key problems? Should we be focusing on prompt engineering and fine-tuning as the key topic of a PhD thesis?
We'll probably see a resurgence of the English departments.
Well, I think that's very hard question. I think that varies a lot, like depending on the location and their funding situations. And some university may have enough resources and to do that, but it's not like F equals MA. Like then is resources. So I think they might limit some educational part, I think.
I think we're also in a local optimum. I think we're still 2 advances away from actual nice systems and models, and I think there's a lot of fundamental issues underlying those LLMs that really need to be solved. I mean, you don't necessarily have to solve the LLM itself, like basically training. I mean, a lot of the performance and a lot of the contribution is in the training part and the pipeline and the adversarial sampling and all the data sets, right? But I think there's also underlying fundamental models that could be different.
I don't know if the robotics, it's the role of the robotics community train and fine-tune these large language models. And of course, if they are related to, I don't know, control or more perception focus, not only vision. Yes, well, somebody will have to start building them, and then people will chip in more and more. But I don't think. Well, it will come eventually, right? At the moment, I still ask my students to learn the maths and the models, and then combine them.
Kaveh, should we take another question from online?
So we have a lot of questions. Definitely won't have time to go through them, but I see sort of a trend of questions about sensors that we're going to be using, say, in the next 5-10 years. And so event cameras are mentioned. Questions are we going to be using them? But there's questions like more general, like any other sensors that you can think of that we should probably be starting to use and do research on.
Maybe I can start. I think David should be there for the event camera. But I am using a lot, like Chris also talk about the radars, but I really like how the radar works robustly regardless of the weather situation. And we are seeing many more sensors upcoming. We used to have only couple of LiDAR sensors, but now we have all variety of the LiDAR sensors, and some LiDAR even give you velocity now. So I think we will see in upcoming years, we'll see more and more new sensors coming up. So as for my point of view, I can tackle in two different ways. I can develop a new sensor model, mathematical derivation for that sensor model, and also I can look into how I can prepare the data set for the training, because that's a new sensor. So there's not enough data set for the training. So so quick question to your question. There will be more sensors coming up, and the new sensors are coming up that will give us a new opportunities.
Yeah, for me, it's also the very same. Information never hurts, right? The more sense. Still, the key question is how to optimally use different modalities. And this is an interesting question which I briefly tackled in my presentation, right? So you basically, whenever you train a model for a sensor, right, then all this needs to be calibrated, and you need to have proper regularizers to fuse the information from the different sensors. And that is something that we, from my perspective, should focus more on, actually. So, because that will give us a flexibility to whatever comes up in terms of a new sensor, but also could be new interpretation approaches, semantic whatsoever, right? Or you name it, and fusing this in a proper fashion is actually still an open issue.
Yeah, I mean, we should have more and more sensors, and that's gonna give us that's gonna give our robots the capabilities that are beyond human capabilities, right? Like if we start using hyperspectral cameras, I don't know, magnetic sensor, acoustic, audio sensors, well, like the human, that like new and more modalities is what's gonna kind of push that frontier from what robots can perceive today. All for new sensors.
Are there more questions from the audience? There's a question over here.
Yeah, so 2 days ago, Google released this super big open X embodiment model that praised for generalization across 22 robots. So I'm wondering what are the panelists' thoughts about how to maybe scale up the data for robotics? What data should we scale up and how do we scale up the data? What is the internet for robotics? Like, yeah, thanks.
So I think simulation plays a big role. I think for this, it's just not feasible to have robots running all the time unless you have them out there, like so Tesla or some of these companies, right? But I think simulation or taking your real data and creating some virtualized set of scenarios to increase your data set is probably key. And but at some point, the simulations are not realistic enough yet.
So adding on that part, so you can actually use a generative model like translation, image to image translation to generate thermal image labels, which was not there actually, just picking it from the RGBs. So you can use actually the deep learning to generate model for you. And also we are using robots, so we always have not only the data, sensor data, but also we have some movement data from like kinematics or autometrics, where those can give you can be used as a guideline to train the other sensor modality.
I mean, I think this work is that you mentioned that is actually a very interesting idea, and we as a community we should maybe carefully think about this as if we shouldn't invest in this as well. I mean, we have so many robots, right? And everyone has a robot in her or his lab, and the question there is like, can't we have a better way of sharing these machines so that we actually get more data for learning, right? So that we get rid of like everyone optimizes something for his or her own robot. That would enable us to basically share our robots with the world and have a community effort. Otherwise, the risk is going to be that there will be big companies who do exactly this, right? They sell their robots, they have their own like access to the database, to what the robots do, to all the images, to all the controls, and then they are going to do that what we actually want to do, right? So basically having the data available. So I mean, we see this now with the large language models or the vision language models, as some of the computer vision tasks are all of a sudden not that attractive anymore, right? So and that shouldn't happen to us, but the risk is there that like they do the very same they will do the same with robots in the future that they have been doing with the phone already, right? Where you have various functions that just are being learned from the data that we provide to them by using the phones. So I think, at least I would like to make a statement here that might be worth thinking about, that we as a community build like actually a tool for doing exactly this.
There's a question on this side.
Yeah, so I guess I have an inverse of some of the questions we've been asking, just because I think it's interesting and helpful to keep up with where we're going. But maybe in the last 5-10 years, thinking about that, where do you think now that there are applications for robots for people in academia who would like to use a robot to further their own research? Maybe their research in biology or their research in some other area, where we're starting to see robots being used as research aids where the robot is not specifically the focus of the research.
Well, so before joining, so I was at the civil engineering department for 7 years, and civil engineering sounds like quite far from robots, but they are actively incorporating many robots to guide the construction and use the SLAM specifically to monitor the changes if the construction process is ongoing properly or not. So I have been seeing that kind of thing. That's one application I think I can mention.
maybe one way to think about it is like the lower bar is data collection, or essentially getting data quickly, and then moving up from there is doing some manipulation, some tasks, right?
I think in arts and robotics are now starting to come together more seamless. So that area has probably pushing a bit more than other that require more reliable deployments. But yeah.
I'm sorry to say that we're already running out of time, so maybe we can do one last question and then go for lunch. So who wants the last word?
Hi. Thank you again for the panel. I had a question regarding if you've ever explored, coming back to the talk about sensors, exploring into the remote sensing side of things and incorporating that back into fusion models. I guess some of the complexity there involved with is you have a much higher amount of dimensionality now adding into that. Is that something that you've considered or something for future work?
And I think remote sensing can give you a lot of information. I mean, we mainly use it for localization purposes, but I mean also for traversability, for off-road driving and that kind of thing. But I think it can give you can also get, I guess, temporal changes over time, which should also be useful for generalization. I think that and getting more and more of these like up-to-date data sets, I think that's actually a good idea.
I mean, if you think about like robots being basically moving sensors, right? Then so there's two things that I find interesting to look at. The first one is learning from humans, right? Which is you can do this in a human-robot interaction context, but you can basically also using these language models is kind of like learning from humans as well, because it's our input that these models have. But at the same time is this entire concept of fleet learning, right? So how can you actually optimize your robots based on data from other robots, which is also partly tackled in this paper that was mentioned, because they're doing even transfer from one robot to a completely different robot, and which goes a little bit beyond this remote sensing where you have a uniform a fleet of sensors somewhere. But I think that this is very similar, and the question there is how we can actually like update these models that we're having either about the world from different sensors or about the sensors themselves, right? Based on the data that we get, and basically enable situations where this entire system gets better every day. That's what you actually would like to have, and this is where I think the future will be, because if you really believe that we will have like millions of robots in the world in users' homes, then this is exactly the functionality that we want.
Right, let's thank our panelists for their time and insights. Thank you. Enjoy a lunch break. We're going to resume at 1 o'clock with a talk from Michael Kaess. So that's going to be exciting. Try to be back.
Alrighty, folks. I think we are going to start with the next lineup of talks. We have a bunch of exciting speakers and not a lot of spare time. So we're going to kick it off even though folks are still trickling in. My name is Kevin Doherty, and I will be your session chair for this afternoon. I'd like to welcome our next speaker, Michael Kaess, who is an associate professor at the Robotics Institute at Carnegie Mellon University. Thanks. Welcome, Michael.
Okay, thanks, Kevin. So today I will talk about some non-conventional sensors, and you saw some talk earlier today on radar. So I'll include here sonar, underwater domain, something that we've been working on for a while, and there's a lot of similarity between the two. So first question is, why do we care about sonar sensors in the first place? And that's actually the question I asked myself 15 years ago, when I started on a project for underwater. And it became pretty clear pretty quickly when we did experiments, cameras are not very useful underwater, right? In many environments, if you don't go to coral reefs or so, you have no visibility, right? And you have to be very close to an object before you see anything. Like the image here at the bottom, there's actually the robot touching an object. So sonar, on the other hand, is not affected by this. It can just look through the water in any turbidity, any condition. The challenge, of course, is it's a very noisy sensor, so even very expensive sensors provide you fairly noisy data, and so the question is how to make sense out of that. So what are the challenges here for doing localization and mapping with that? The first one is there are no good features or descriptors. So if you think of typical feature-based SLAM, you can start with maybe looking at computer vision features, as we did, and most of those don't work. So the community basically found only one feature, Kaess, that happens to work with the high noise, with the speckle noise that you have in sonar. And they are not very good. So the question is, should we create features and descriptors? Took the vision community decades to get there. So that's probably not a good idea. Recent learning approaches, of course, can quickly get you to similar level of performance. So we should do that, obviously, with sonar. The problem there is the next challenge. There are no large data sets available. Basically, there are almost no data sets available for sonar. It's incredibly difficult to get ground truth underwater. Radio waves don't propagate. There's no GPS. So you have to do everything acoustically. So this limits the learning options that can be used here. And then the next challenge is sonar geometry is different. It's actually somewhat related to computer vision, right? So it's a projection in computer vision, and with a camera, we lose range information in the projection. With a sonar, similarly, we lose one dimension. We do measure range. We do get the X coordinate, but the Y coordinate is gone. So basically, don't know where an object is along an arc. So the problem is essentially not bundle adjustment, where we have viewing rays that you need to adjust, but it's arc adjustment. So you have multiple arcs that intersect, and you have to adjust these. So obviously we can, as we did several years ago, you can use some of the computer vision methods, structure for motion, and so we introduced acoustic structure for motion. Same idea, multiple images of the same scene, and you can get 3D out. You know where the feature points are by optimization. The optimization problem, some of the challenges are degeneracies, similar as with vision, right? Parallel rays don't intersect, or the intersection is pretty poorly defined, nearly parallel. And so similar with arcs, you have these problems. But you can get around that. You can model this correctly. You don't get the landmarks fully reconstructed, but you can still get localization for the robot, which is the really interesting part. But the tricky part is, how do you get these features? Initially, we even hand selected these and hand corresponded these, which is not very viable. So if we look here, correspondences, this is basically the state of the art that everyone is using. Underwater is Kaess features, and they are not really great for this. I mean, they were not meant to be used on these images. We also tried learning-based approaches, Super and LightQ. Doesn't deal very well with the changes in viewpoint. The appearance in the neighborhood of a feature changes very differently from computer vision side. The geometry is different. So here's a recent work that we call Sonic that learned the correspondences, and that actually works well. These are correspondences before any filtering in all of these cases. Okay, so the basic idea here is we need some supervision because we don't have ground truth, we don't have labeled data sets. And so we went again to the computer vision community. There's an interesting paper on learning feature descriptors using camera post-supervision. So basically using epipolar geometry in vision to guide where you can find corresponding features and to automatically learn that. So we can do something similar for sonar. Scherer and Nikolay actually introduced epipolar geometry, or the equivalent for sonar, which is you're essentially projecting an arc into another sonar image, which gives you some strange curve. But we can easily do this by sampling, and we can then limit the search region and do essentially the same thing. And so with this, we can learn cross-responses. You can here see the difference between the standard approach that we've been using so far, Kaess, and then our new matcher. This is a simulation environment in Hollow Ocean, an underwater simulator. Kind of a strange environment. It's an above water environment that we placed underwater to have a lot of artifacts in here, a lot of interesting features to work with. But so we also did this in real experiments. So here's a test tank experiment with some features at the bottom that come from other experiments in the tank. And again, you can see the feature correspondences are quite good here. What is difficult to appreciate in this is it looks like there's no rotation in the viewpoints, because this part of the structure up here is always the same. But this is actually artifacts from the sonar. So the phased array of the sonar creates some artifacts, especially in a water tank in a symmetric environment. So here we actually do have changes in rotation also. And that's why the correspondences seem a bit off at times, but they're actually correct. So, and we can also look geometrically here on numerically, percentage of inliers. If we compare, we significantly outperform what was used before in the field. And we can also evaluate the relative pose error. So in this case, we use the correspondences and do the acoustic structure promotion, or really just the optimization part. So acoustic bundle adjustment should really be called acoustic arc adjustment. And so again, we significantly outperform the previously used methods that we previously also used in terms of geometry. So good. So this gives us localization. So now we can figure out where the robot is. We get some sparse features, but they're not useful in terms of mapping. So we've recently introduced a way to do dense mapping with imaging sonar, which is learning based. So here we tried a number of different things in the past, and then my student had the idea, let's throw nerve at it. And that actually worked wonderfully. So it's different geometry. It needs a bit of work to adapt, but basically it's a similar idea. Neural implicit function here represents the surface. We have to define a differentiable renderer for the acoustic case specifically, and then key importance as in vision adds regularizers to that. And let me actually skip over this detail. The sampling procedure is interesting. So in NERF, you typically have to sample along viewing rays. So in this case, you don't know along an arc where an object is. So you actually have to sample along a slice through the environment. So you sample an orientation and then sample along a ray. So it's relatively easy to adapt. And the only other thing that has to change is the image formation model. There are a couple of additions coming in here, a couple of differences from the vision case. So at the end, the training loss then is the geometric part and the regularizations, iconolars and a regulator to make everything smooth. And so with this, here are some reconstructions. And if you haven't seen sonar reconstructions before, they're pretty poor. It's really difficult to get good stuff from imaging sonar in particular. So this is in simulation. You see the crunchers at the top. Two other methods, one of them that we introduced here, and then our new method down here, which significantly outperforms what was there before. You can actually see where the object is here. And in real experiments again, in the test tank. So here's a test structure that we created to put into the tank. This has a bit more interesting topology than something you would find in infrastructure like pilings under pier with cross beams and so on. And we took a laser model of this to have ground truths available so we can compare. And so here are some of the results from this. The columns here are the aperture of the sonar. So there are different kinds of sonar. There's a 1 degree, very kind of fairly well defined where the geometry is. These are profiling, also called profiling sonar. It's very slow to map something with them because you only get a small slice and acoustics is pretty slow compared to laser. And then here, these are the more common ones, 14, 28 degree wider opening angles. And so we're still able to recover the topology even in the extreme case here where previous methods completely failed. Our previous methods here completely failed. Switching from underwater to air. This seems like an abrupt switch here, right? Radar rather than sonar, but it's actually the same thing. It's a phased array at the end. So specifically, we're looking at millimeter wave radar. Chris earlier talked about that also. So this is a TI sensor specifically. There are a couple ones around. They are using the sensors that are used in cars for collision avoidance, but in this case, 4 different of these chips that are cascaded together. So you have basically an antenna array that is larger, more antennas than in the standard case. That gives you better spatial resolution. And so one other difference to the sonar case is they actually also do get Doppler velocity out of this. This, by the way, also related to some of the laser sensor that was mentioned earlier. That gives you velocity. That's also a phased array sensor. So this is an upcoming sensing modality. So the cool part is it's solid state, right? It works without any light. It works in smoke and fog. If you do this indoor, it's privacy preserving, right? So this is also nice. We have been able to do mapping with this. So here's a setting where we can walk through an environment with a radar sensor and an inertial sensor. We get a map of the environment that's kind of noisy, but you can see the corridors quite well. And we can localize quite well. So the trajectory has relatively low drift. You can see some duplication here of the wall. So there is drift accumulating, but it's quite small. We also have loop closure in place, so we can actually fix that. So we can do full SLAM with us, not just visual inertial odometry. What you do not see here, though, is there is drift in the Z direction. So the height is drifting because this specific radar distributed most of the antennas in the horizontal direction to get good resolution and only a few in the vertical one. So we overcame that, a bit of a hack at the moment since there are no good other sensors out yet, but I think this will change by simply using 2 of these. So we rotate one by 90 degrees, have to reprogram them a bit to use different frequency ranges, but we had to reprogram them anyways to do short range indoor and get better velocity resolution compared to what you typically do for cars. And so with this visual inertial odometry, now also including stairs, which we couldn't do before, you have almost no drift. Some more sequences here through different environments, even a spiraling ramp here. And so all of this works quite well. We can also compare against visual inertial odometry. And here you can now appreciate in green is the original horizontal only configuration. So Z drift is quite significant. In red is the next thing we tried, right? Turning it 90 degrees. And in fact, it gets rid of the Z drift, but you get much more XY drift. And then the dual configuration is pretty close to the visual inertial case. So just using the radar sensor and inertial, we can basically walk through an environment and know where we are. We can also do mapping with this. The map, though, here is built using the typical way you do target detection in radar, so C4 detector. We have played with learning-based methods, but so far we haven't really succeeded in making that work. There should be enough information okay, it's not clear if there's enough information to actually map surfaces. What you see, a lot of the structures are actually inside walls, the support structure, which is what the radar picks up. But there may be enough information. In fact, there's a huge amount of information available if you look at the raw data of the radar before FFT is being done to get the intensity side with which we typically work. But these are also huge amounts of data. So that's a sensor that produces enormous amounts of data compared to others. So in summary here, I talked about the sonar side where we did learning of correspondences. We used neural rendering to do dense mapping. In the radar case, it was actually mostly classical methods at the end. What we tried with learning, kind of with laser supervision, for example, was kind of marginal, didn't result really good, didn't provide really good results. So dense mapping is still an open problem here. But I think that's one where learning is probably the only good way to make this work. On the back-end side, I haven't talked about that part. We have actually used mostly classical methods underneath. So this is the standard post-graph optimization or factor graph optimization methods. And since I still have a minute, I want to quickly advertise. So we've recently published a robust method for optimization. This is using the graduated non-convexity from MIT and making it incremental. So instead of a batch method, be able to incrementally apply that. And that required a couple other changes. But so this is basically outperforming all other methods that are out there and in a pretty detailed evaluation. And also soon to appear, or some is already on archive here, both asynchronous distributed smoothing and mapping. So all of those completely classical methods. I think deep learning hasn't really had much of an impact on the optimization side, on the backend side, because we simply know how to do this, right? But the one thing we don't know is how to characterize noise. So we can also learn that, learning covariances. In this case, in a way that the resulting covariance matrix is guaranteed to be well conditioned, right? So you can actually have constraints on that. But it's, again, kind of a classical optimization method, no deep learning involved. Okay, so yeah, with this, I'm happy to answer any questions you may have.
Yeah, so great talk. I know so it's like speed of sound in water is quite a bit slower than light speed of light. Does that introduce any additional problems with like motion distortion? And if so, how do you handle that?
Yeah, so this is actually one of the challenges. Speed of sound is much faster than in air, luckily, in water. So it's 1,500 meters per second, roughly. But that's still really, really slow compared to laser scanners can image much faster. So this means doing a single slice will actually take a bit of time, even if it's just a few meters. And so this means you cannot quickly scan different slices. And so that's one of the challenges actually underwater and why the imaging sonar is relevant, since you get the whole volume imaged in one go. The effect is mostly that, for example, salinity changes the velocity pretty significantly. So you have to compensate for that. You have to measure actually salinity, temperature, and use that to compensate. Other than that, unless you have pretty high currents, that's usually not an issue, right? So currents, typically a meter or two per second, that's relatively small in comparison. Yes?
I'm wondering, thank you for your talk. You have to look at sound underwater and radar over water. Have you looked at sound over water, like in echolocation?
We actually have not. This is quite interesting. So I was thinking about this quite a few times, right? Bats actually use this to localize. There don't seem to be any sensors just because there's so many alternatives, right? No one really bothered about making these sensors. But there would be even further disadvantage because of the slow speed of sound. So you're another factor 5 off there. Yeah, there's just too many other good choices. It's really underwater where you have no other choice.
Okay, I think. Our next speaker will be Joydeep Biswas, who is an associate professor in the Department of Computer Science at the University of Texas at Austin. Welcome, Joydeep.
All right, cool. Let me get started. So I'll be talking about some approaches towards context-aware robot navigation, right? So what do I mean by that? So I mean, how do we deploy urban service mobile robots? So on the left, we have some robots at UT Austin, including indoors, the Cobot, and the outdoors, we're doing package delivery with the Jackal, and we have the Spot also autonomously driving around on campus. And we're also interested in like the kinds of problems which might be faced by like the Astro or the Diligent robots and many of these robots on sidewalks, right? So what are these problems that these robots encounter, right? So I'm going to walk through a couple of them. So here's a snippet taken from this data set, which we collected. It's called the Socially Compliant Navigation Data Set, right? This includes a couple of, a lot of very interesting examples such as this, where the robot, if you ask a geometric navigation planner, like it plans its trajectory in red, whereas a human is trying to carefully avoid this grabber, right? So this is one example of context-aware navigation. There are others. One example of this is that you need to cross a street, and if you care only about geometry, you can just go straight across the street, which is actually unsafe. But a human would cross at the crosswalk and cross there, right? This gets even harder when there are environments where you don't have marked crosswalks. So this is actually a crosswalk, but it's actually not labeled. And the human can infer that by noticing that, look, there's a sidewalk and it like leads to the road. There's a curb cut. So this is probably the correct place to cross, right? Here's an even harder scenario. So here's a scenario where the robot's driving around in a cafe, and the geometric navigation planner decides that it's going to go behind the cafe into the private area and like cut through it, right? But that's not what a human would do at all, right? So this is actually rather difficult. Like, how does a robot reason about the fact that you're not allowed back there, right? And here's an even more interesting example. Here's a queue of humans waiting for to buy something from a food truck. And then the robot is trying to just avoid the queue entirely, whereas a human knows that, hey, if you just come up to the queue, then people will let you pass, right? So the interesting thing that I want to point out is that there's many different kinds of contexts that these robots need to be aware of, right? And you can have increasing levels of complexity. And if you really, really, really wanted to, you could do them with geometric navigation and tedious manual map annotations. The disadvantage of this, of course, is that you need to have very precise localization. You need to tell it that, okay, at this location, you're not allowed to take a left turn. At this location, you're not allowed to do this. It just doesn't scale, right? Instead, what we want to do is that we want to have no reliance on this precise localization or detailed maps. And we want to have robots that make these decisions during deployments, right? Reasoning about observations and inferring context, right? So two key sources of context that I want to talk about are object detection and tracking and terrain awareness, right? So first of all, right, you might ask this question, hey, you care about objects. I've heard about these things, these large AV data sets. Why can't we just use them, right? The answer is very simple. This is an urban robot. On the right is an autonomous vehicle. This figure is drawn to scale. This is actually a cruise vehicle, which we get to see a lot of in Austin. The scales are very different. Their viewpoints are very different. The sensors that you have on the AVs are very different as well. And the entities that you care about are quite different. And I will show you some quantitative results to convince you that you shouldn't be using AV data sets for robots, right? So to address this problem, we actually came up with this data set called the UT Campus Object Data Set, which is led primarily by Arthur Zhang, who's a PhD student. Arthur's right there. You're welcome to address questions about CODA with him. This is, as far as we are aware, it's the largest multi-class, multimodal labeled data set for urban robots, okay? It's not robots inside, it's robots outdoors. So here's just a brief snippet of what this data set contains. It's in challenging environments with 3D bounding boxes. We have synchronized cameras and we have depth cameras, right? So this is the platform that we use to collect this. So we have a 128 channel LiDAR. We have RGB cameras. We have actually 5 RGB cameras, which we have access to, right? And we also have an IMU. For every sequence, we also include calibration. So here's Arthur moving a checkerboard around. And although we provide the calibrations for you, you're welcome to fine tune the calibrations. As an example of, as a test to show that these calibrations are actually quite good, you can see that the point cloud agrees very well with the images, okay? And we get a lot of diversity in terms of places. So we have places with hybrid traffic, open areas, cafes, road streets, libraries, etc. But what's even more important is that we visit the same places under many different conditions. So we have, for example, this location, which has sunny, cloudy, and rainy. The same location, sunny, cloudy, rainy, and dark. And in dark, you can see actually looks quite different, right? So if you wanted to train the models to cope with these variations, this would be a good data set for you. Here are some more examples of viewpoint invariance, so showing the same objects from different viewpoints, from drastically different viewpoints. So here's one entity of a label for a shop, which is seen from different viewpoints and so on. So we have quite a lot of scene diversity in terms of both weather conditions as well as time of day, right? If you care about like the objects, we have a very large number of objects that you care about for situational awareness for robots, and dynamic objects that you might care about, right? And for every object, we have a lot of variations of different conditions, including cloudy, dark, sunny, and rainy, right? This is for objects, right? Okay, so for terrains, we also have a lot of terrain labels available to use, including, I mentioned the sidewalk. You will see that we have labeled sidewalks as well. Okay, here's an example. And again, we have quite a lot of diversity over this. For those of you who are interested in large-scale mapping, we also provide registered global poses for every single trajectory. And this video just quickly shows a video of all of these trajectories, actually 4 trajectories overlaid on each other and on top of the map. Okay, so let's dig into this data set a little bit more and ask these questions. So how well do object detectors trained on AV data sets perform on CODA? How is object detection performance affected by differences in resolution, LiDAR resolution? And how can we actually transfer between different data sets? Okay. So over all of these, we're going to use the average precision with bird's eye view, and we're going to use the intersection over union and the threshold over here is 0.5. Okay. So first off, right, so in this table, you have pre-trained models from New Scenes, Waymo, and CODA, and all of them are evaluated on CODA. So you can see like direct transfer from these AV data sets, of course, has like a huge performance gap, right? So the CODA model gets like 92% accuracy, whereas the New Scenes and Waymo have 21 to 46%. You get the best performance, of course, if you fine-tune. So pre-training on Waymo and fine-tuning on CODA gets the best performance. And this column actually shows something interesting, which is that if you do unsupervised domain adaptation without labels, this is actually quite counterintuitive. You actually get worse performance than if you're just done direct transfer. This actually is not something that's unique to our data set. It's been noticed in other data sets as well, but it does lead to a question of how can we do this better. Okay. Here's a table of training and testing on different resolutions of LiDAR. So if you have trained on 1632 to 128 channels, what is the evaluation result on these different resolution LiDAR? So it might seem to you like if you train on a low resolution LiDAR, testing it on a high resolution LiDAR might get you better results. It's actually not the case, right? So for every resolution, it's best when tested at the same resolution. And of course, the performance increases the higher the resolution you have. Okay. And by the way, we have pre-trained models for all of these available for you. Okay, so to evaluate how well these data sets trained in our setting transferred to other robot scenarios, we actually took the pedestrian detection from CODA and tested them in GRDB. And we actually get quite comparable results directly out of the box, no fine-tuning, despite the fact that we have a lot fewer pedestrian labels than these other data sets. Okay, so from this section, my key takeaways are essentially that object detection transfers poorly from AV to urban environments, right? The train test resolution match is very important, and robot to robot transfer performs a lot better than AV to robot transfer. Okay. And finally, if you're interested in urban robot settings, please feel free to use CODA. Okay. Here's a link. Okay, so I want to switch a little bit to talk about some terrain-aware navigation work that we've been doing. So here's an example of that. So let's say you deploy a robot on campus. You want this robot to like follow the sidewalks and not drive over the grass or like the gravel, right? So how do we do this, right? So in this work, in this line of work, the way we do this is that we have an input image. We actually come up with a homography transform to convert it into a synthetic bird's eye view, right? For every patch over there, we're going to pass it through some learned visual representation function to come up with some terrain embeddings. And then from there, we'll derive a cost function, okay? So the pipeline looks like this. Image patch through a learn function fviz to get an embedding vector, through a cost function to get a positive cost. Now, the question is, how can we learn these, right, without labeled training data, without hand-coded cost functions, without structured demonstrations, without experience on unpreferred terrains, and without experience on deployment terrains? Now, of course, this is actually very hard to do with all of these constraints. And I'll talk a little bit about a few approaches where all of them satisfy the first two, right? We don't need labels and we don't need hand-coded cost functions, but we will have to relax these final three assumptions a bit. Okay. So first, let me just give you an example of some work where we did where we actually come up with representations for preference-aware path planning from unlabeled human demonstrations. So what does it look like? So let's say you're teaching a robot to navigate in this environment. The human demonstrates this path, right? But until the robot actually learns to infer the differences between these terrain, as far as the robot is concerned, like this is all it has available to it, right? And the robot can then hypothesize that if it only used geometric navigation, it could come up with these shortcuts, right? This is actually quite useful because it actually provides a counterfactual source of information. So then the robot can reason about the fact that you can extract a patch on the human demonstration and on the hypothesized shortcut and say the visual embeddings between the two of them must be different. It doesn't know why it's different, but it's different. Okay? So this is actually one crucial piece of the puzzle. The second piece of the puzzle is that let's say you have different views of the same location in the world. So the green patch over here is the same location, it's just viewed from different viewpoints. Since you're reasoning about the same location in the world, the visual embedding of the two must be the same. Okay? And combining both of these ideas, you end up with this contrastive constraint, which you can convert into contrastive loss, which essentially says the visual embedding between the anchor and dissimilar must be at least this delta away from the anchor and the similar, right? And then finally, using this demonstration from the human, you can actually also recover the cost function such that the cost of the human path is less than by some margin delta C compared to the shortcut. So this actually does work out quite well in practice. So with only a few minutes of demonstrations, we took the robot out to the park and asked the robot to just continue following the trail. We didn't actually give it a goal. We just told it just follow the trail. And you can see on the left, these are the input images. On the right, you have you can see the terrain representations in false color and the cost maps over there. You can see as it's going into and out of the sunlight, there's lighting variations, but this representation is actually quite robust to that. And this is without any labels and with only a few minutes worth of data. Okay, so what if you said that you didn't like the idea of like human demonstrating paths, right? What if you have unstructured demonstrations, right? So in this work, which we're actually going to present at CORL, this is work led by Harish, who's a PhD student, along with Elvin and Daniel, on how can we do unsupervised representation learning. So the challenge of unsupervised representation learning is that let's say you have vision data of a sidewalk. They can look actually quite different. Now, if you do unsupervised learning, you might be tempted to like segregate out this patch from like this patch as like different types of terrain. And in fact, even things which look visually distinct or similar might actually be misleading. So for example, this green thing is very similar to the bush, and this brown thing is also still grass, right? So how can you actually take into account these differences? So the way to do this is actually to use multimodal data, right? And here's how we do this. So let's say the robot's reasoning about this patch in the world, right? And if you look back in the history, right? So the robot saw that patch from different viewpoints. So it gets two different visual information. And as the robot's driving over that patch, it actually captures inertial, proprioceptive, and tactile data. So using these three inputs, for example, you can actually come up with a constraint, so which says that the input images of the same patch in this setup will end up with embedding Z1 and Z2, and the inertial proprioceptive will end up with ZIPT. And essentially what we say is that all of these, since they're all different views of the same patch in the world, they must be the same. Okay. And so the unsupervised learning approach is essentially to, the constraint is that whatever you do, these need to be invariant. Okay. And this problem has been studied extensively in unsupervised learning. Some of the early work on this was with Barlow twins. More recently, there was this work on VicReg, where essentially the idea is to have variance across samples be preserved. You want to have covariances across the features be minimized. And you want to ensure that the encoding is invariant to modality. Okay. So you could apply, say, VicReg to the visual inputs, right? But essentially what we do is that we actually have constraints such that the embeddings across the vision and across the inertial proprioceptive sensing are actually the same, right? And you can look in the paper for more details about how we do this, but essentially we share the same projectors for both the modalities. We just have different encoders for inertial proprioceptive versus vision. Okay. And here's just a very quick visualization of the embeddings just projected into 3D. Okay. So once you have this, you have essentially unsupervised clusters of different types of terrain. We don't know which one's preferable or the other. And this is where the operator comes into say. The operator can just use a GUI like this and say, like, come up with like partial ordered preferences. Okay. So in the interest of time, I'm going to switch to just some qualitative results. So using this model, again, we deployed this extensively on a large scale environment. This is a trail. And on the right, you can actually see some interesting out of distribution responses. So the robot hasn't been trained on this water, but it knows to like avoid it in this scenario. Okay. Okay, so this is how you do this if you had experience with all the terrains that you're deploying with. But what if you don't have experience in the deployment terrain, right? And the idea behind this approach, which we call pattern, is again led by Elvin and Harish, is to leverage similar inertial tactile responses to perform self-supervised adaptation. So how does this work? Let's say pre-deployment, you've trained on 3 different types of terrain, okay, and your visual encoder and inertial tactile encoder end up with like 3 clusters. And during deployment, you see this new type of terrain, which in the visual space is just all over the place because it looks visually quite different from everything that you've seen before. But if you ask the robot to drive over it, the inertial tactile response is actually very similar to something that it's seen before. It's in concrete. So the fact that it's actually well clustered in the inertial tactile space is a self-supervision signal to tell the visual encoder to actually fine-tune it such that it clusters them together, right? And then you can inherit the costs from the inertial tactile representation to actually fine-tune the preference function in the visual space, okay? And here's just a quick video of some results for that, right? So here's an environment where we've deployed this at night where the vision is actually quite different. Previous to the adaptation, essentially all of the models fail. They actually drive over this gravel surface, which is actually kind of dangerous, right? However, after it drives over this, our algorithm is actually to realize that, oh, wait, this thing looks visually distinct, but it's actually quite similar to this gravel thing, which I've been told to avoid. And after adaptation, even in this really difficult visual setting, the robot's actually able to successfully avoid it. Okay, so the key takeaways from this section is essentially that representation learning for terrain-aware navigation is indeed feasible without labeled data. However, depending on your setting, you might need structured or contrastive demonstrations. Okay, and this finally leads to some open questions, which I'll leave up here while I take questions, which is how can we teach robots to learn to identify relevant objects of interest without labels, both robustly and accurately? Right? We've shown how we can do this for terrains. We still don't know how to do this very well for entities or objects, right? And the second question is, do we need to discretely track these entities, or do we even need that for context-aware navigation? And finally, how do we even generalize to out of distribution settings? Okay, so thank you, and I'm happy to take questions. Yes, question.
So for your data, did you mostly drive on flat surfaces, or sometimes you would have slopes, which would tremendously change your proprioceptives and all the IMU stuff? It would really change the signals.
Yeah, so we drove on different types of terrain, including like bushes and all, where your foot actually goes into the terrain, and like dense grass, and also things like rocks, where it's quite uneven. But yeah, it wasn't all just flat things like concrete. Okay.
Thank you.
I think that's all the time we have for questions for now, but folks are welcome to find Joydeep if you have more questions. Next up, we have Golnaz Habibi, who is joining us. She's an assistant professor in the Department of Computer Science at the University of Oklahoma. Welcome, Golnaz.
Okay, great. Good afternoon, everyone. Today I'm talking about the future of advanced mobility, and I'm focus on the low cost and onboard sensing and processing and collaborative decision making. And I'm talking about a little bit about our mission in our lab, which is Autonomous Interactive Robotics Lab at University of Oklahoma. And our mission is to create and build a there you go. Build a team of the heterogeneous system and robots for emergency response in general and for solving in real time, real world challenges. And we focus in different domains, including visual navigations, advanced air mobility in general, multimodal localization and mapping, and multi-agent systems, and also communication. So I start with what's our motivation about the emergency response. As I'm living in Oklahoma, we have a lot of unexpected weather situations and many different cases, for example, tornadoes or even flooding. And also we know that in, for example, different areas in United States and all over the world, for example, we have a flooding and wildfire. And the question is that how we can basically our mission is that how we can create a real-time collaborative and basically robust advanced air mobility in general, and in combination, in collaboration with autonomous ground vehicles, such that we can respond to these emergency situations during, after, and before these disasters. And actually, there is a project funded by NASA that they are leading this project. They call it basically a data reasoning fabric, or DRF in short. That as you see that here, basically we have a connection between the cars and the vehicles, the aerial vehicles. I'm trying to use the laser point. So seeing that. Basically, they created this data interface such that every vehicle or every from the smart city and every agent, including the people and also the autonomous systems and also any smart cities and any smart infrastructures, they share this information and also they get some other data from, for example, weather situations or about like the geography and different parameters, and then or about from the, for example, weather forecasting, National Weather Center, and they make a decision. So this DRF is responsible to make a decision and then send this planning output to the different agents that is involved. But of course, there are many components that we need for building this emergency response. Basically, we need to consider an accurate and also, of course, real-time response for this collaborative planning and perception. And basically, this talk, we talk about the solution is that using data reasoning fabric, such that the platform that we have, we can share the data between the all advanced mobility, such that we can have a real-time response. So I start with one of the very simple example I did during my PhD, that showing that how very simple robotic system can do the collaborative perception and planning. So in this video, I'm trying to use that. So this video is showing that the simple scenario is that how we can use our robotic system for the search and rescue scenarios. And all the robotic system here, they're coming together and actually create this path between themselves and do all the perception and planning such that they can carry this object as a, for example, human example to, for example, in some situations that we cannot have a human being there. So this is a simple example, but we inspired with that to create this more larger scale. And our goal is basically having, again, the low power and the low, in general, low cost, and also, of course, in general, having the real-time systems. But it also requires not just the sensing and processing involved, and also we need to consider the reliable communication and, of course, a safe and efficient navigation. For doing that, basically we use a specific processor here. So it's a neuromorphic design, and it's basically in this one, sometimes talks. Yeah. So here it shows that basically our model, we can consider this new technology that it is inspired by the real neural network, such that you can build and create this chip. They call it neuromorphic chip. That is, they use it for as an edge technology. An edge device is much faster and much is lower in terms of the power, is low power. So we use this technology for our edge navigation and edge devices, AI edge devices. And also, in terms of the low power and robust sensing for advanced mobility, as we see that, and we see in many talks today, and in general, we have a lot of advances in cameras and the LiDAR and other sensors, but we know that the problem with the camera and the LiDAR is that they are not, and any other light-based models, that they are not robust with different illumination as well as the weather situation. So we are interested to use radar, that we also see that today in different talks with Dr. Kaess and also Dr. Kim, that they mentioned about it. The radar would be a future of our sensing, at least having as a combination with other sensors. And here's just one of the papers that is one of the famous papers, Radar Slam, that for all weathers, that they use this small, for I think one of the first work that they did the Radar Slam in the actually using the machine learning techniques, and how they can use it basically for the SLAM problem. But our goal is actually to have a combination. We don't say that we don't need other sensors. We combine all the sensors together, but depends on our application and problem. And there's other works that basically I'm reviewing a few works and showing that, okay, what's the current work. This is paper that I got from CBPR this year, 2023. One is focusing that, okay, if we know that the problem with the radar is that low resolution and sparsity, basically. So for solving that, there are some technology that are using machine learning techniques that, for example, to kind of hallucinating and adding some extra rays such that you can add denser and having denser model for that. So this is one of the work that's showing that basically in this figure, from the top to bottom is the input. The original one is very sparse, but they have this hybrid model, and compared to the ground truth, we have a much better result. But of course, still we are new in this, and we need, there are many open questions to solve it. I mean, to improve that. And the other problem is that in terms of the radar is for the how we can use it for the depth estimation, because we know that depth is important for having the mapping and also object detection and tracking in general. The good news about the radar is that they don't have the problem of the reflection from different objects similar to, for example, the LiDAR and cameras, and we can see that we have this type of the behavior as a blue line as your reflection of from the radar. And but now question is that we know that the radar doesn't provide many resolution compared to camera and many texture. And the idea from this work is that how they can combine the camera and the radar together to get a much better depth estimation, basically. And this is the network that they use it, so I move on. But The result actually, we saw that at some part that is basically still because radar doesn't have information about the semantic of the environment. So we added actually here, this is our work that is in progress, that we add the semantic to this work to improve the radar depth estimation. So this is from the video from the basically the image on the left side from nuisance data sets and how we can create a depth map using the semantic guided radar-based perception. So usually the closer is darker and the further is brighter, as in this picture and the video. There's other example, continue that, but just move on. This is also be a size of increment. That one that we see that is a different radar, but this one, the millimeter wave radar that I think Dr. Kaess also mentioned about it. So it's basically, we start using that as a very initial work that we have. We have a good facility at OU, is a ARC Center, if you heard about it, is a Autonomous Advanced Radar Research Center. So we are working with their engineers to make use of better use of the radar. This is just the initial result that we got it for the different, from the two planes, so we can create like a 3D information. But as I mentioned earlier, that we need to add some actually some other work, for example, using machine learning techniques and some learning phase to make sure that we have enough and dense enough information from the radar. And as I said, talk about it, the radar challenge, that we see that the radar is beneficial in different weather situations and is usually low power and low cost in general compared to the LiDAR. But challenge that we see that the low resolution in general and some ambiguity and based on the multipath and the other problem that we have in LiDAR. But the idea is that using machine learning techniques to improve that. And also, we don't have the information about the semantics. So now, by fusing the camera and the radar, we can come up with a better accuracy and better mapping and perception. So I move on to the next topic that I'm going to cover. So after the perception and the part of the processing, we need to do the communication and the fusing the model or sharing the data. Our idea is using the federated learning type of the model such that we don't share the raw data. For example, if we have a set of the car that they basically explore the environment, how they can actually share their model that they learn. This model here showing that basically how they can learn from the data, from the trajectory, from the pedestrians at intersections. And the idea is that instead of sharing the raw data, which is maybe huge, we share their learned model. So each car, for example, individually learn from their own model, and then we can share it together in centralized fashion or in decentralized fashion. So the result is showing that here basically we also use another part is basically the transferability. So the idea is that how we can share this model, assuming that the trajectory from different intersection would be affected by the shape and the geometry of the intersection. So the idea is that how we can fuse it efficiently. So the idea is that we use the specific distance to the curb side as our metric for measuring as a feature. So we measure the pedestrian distance to the curb side of the intersections. But we use a specific geometry as a specific measurement. It's basically not a rectangular, basically based on this way of the measuring. They call it a contravariant distance. And if we're having that, if you look at this picture on the left, on the top row, we have two different intersections. We do completely different trajectory, but both of them imply the same intention, which is turning left. right, at the intersection. But if you just want to use this raw data for training, you cannot later fuse this data or merge it or augment it or even fuse their models. Instead, we use this model that I explained to map it and use this new mapping to map it to the new trajectory we see in the second line. So basically, you can have a transferable feature and more higher level feature which implies the intention of the pedestrian, not just their route trajectory. And of course, we can use that for training model and also first fusing and augmenting the data. You see that we have intersections with different geometry, but how we can fuse it at the same map on the right side. And we can have it as you see that how it's happening basically based on this model, how it maps this trajectory. The blue lines are the trajectory of the pedestrians, and the gray area is the curved side next to the intersection. And also, we show that our model fusion is working well. So you see that, for example, if you have a data, if you have 5 agents into these house shapes, and the prediction start with the error of the prediction of the pedestrian trajectory starts the high values, but then they use some consensus and communications to share their model, and eventually they reach the same accuracy and much better accuracy compared to their original model they have. Now I'm going to the part of the hardware of the system. So basically we have our different hardware in our system that we build. We have the autonomous drone and we build from scratch. We inspired with the hexacopter shape and some technology from MIT version or my previous lab at MIT. And then we continue working on that and having our unique design for this. And we have a 2 processor voxel for the flight controller and also the Intel NOC. And also we have the race car. We have 6 race car for now that we have 2 different design by using both low cost sensors like just 2D LiDAR, and also another one is higher cost. We're using the Velodyne VLP 16 pins. And we use that actually for our new city that we created in our lab. And basically, we already have a very nice mini city at MIT, basically in CCEL. But this one has its own features, which is including that we consider collaborative and connected vehicles. And also we consider smart intersection and smart infrastructures. And our city has this capability, has a different building dimensions and different environments. So having said that, for example, even we try to simulate situation that we have, the emergency response, having for example, the drone on the top of the hospital building and the other cars, how they can communicate with this drone, and basically they can do different tasks of the emergency management or search and rescue problem. So here's really a very simple video showing that the smart intersection. So assume that we have the 2 cars here, maybe they are out of the field of view, but by using this LiDAR at intersections, we can send the information to this car. So this car, they can navigate this environment without any collision. So that's the whole idea that we have, having this new city with the collaboration between the cars as well as having the smart intersection and smart perception. And we can use it actually, we have some plan was doing some specific toy shape of the pedestrian, so adding these features as well in our model. So as a conclusion of my talk, this talk covers topics in building block for modules for the real-time and robust and to the emergency response in general and advanced mobility. And we want to improve the collaboration and also communication between the team of the robot as well. But still, we have many problem and an open question, as we also obviously other speakers talk about it, about the sensors, how we can use the best use of the sensors using maybe machine learning techniques or having the good combination of them. And of course, the other thing is very important, scalability. If you want to have a team of the robot, how we can make a scalable team. And just one lesson I learned also is basically we need to choose everything wisely. For example, this is a tunnel that we have it on University of Oklahoma. It's like underground tunnel that we use it as a shelter for the tornadoes. And actually I use basically that one for mapping, but we just use very cheap $99 2D LiDAR for mapping, and it did a pretty good job. So I'm saying that it's very important we consider our problem and our purpose of using any sensors or the algorithms. So thank you so much for your attention. I'm not sure if you have time, maybe I'm right at the time, but thanks so much. But if you have any question, please send me an email and visit our lab website. Thank you.
Alrighty. Last but certainly not least, we have Giovanni Cioffi, who is a senior PhD student at the Robotics and Perception Group under Professor Davide Scaramuzza. Welcome.
So, hello everybody, my name is Giovanni Cioffi, and today I'm going to talk about our work, HDVIO, improving localization and disturbance estimation with hybrid dynamics VIO. So visual inertial odometry is the de facto choice for state estimation of flying vehicles. The accuracy of VIO depends on the camera measurements. When the camera measurements are not reliable, VIO accumulates drift. So recent works have proposed to include new constraints, so new information in the VIO system using a motion prior that comes from the dynamics of the robot. In this presentation is a quadrotor. So these works that I'm going to call in this presentation visual inertial model odometry methods allow to increase the robustness of VIO when the camera measurements are not reliable, for example, when there is motion blur. And also, they also allow to predict external disturbances acting on the quadrotor platform, for example, wind. So in this work, we are considering a factor graph representation of the VIO problem formulation, while visual inertial model odometry methods augment this factor graph representation with a new factor that basically includes the model dynamics of the robot. In spite of working very well in many situations, these methods, the performance of these methods degrades when there is a continuous disturbance acting on the robot, for example, continuous wind, or when the model mismatch is large. This happens, for example, at high speed, when the aerodynamic effects are relevant. This is because of the simplifying assumptions that these methods have in the model dynamics. So here in this work, we propose to augment a first principle quadrotor model that is based on a simple point mass model with a learned component that is able to capture complex aerodynamic effects and systematic error in the platform. So here on this slide, I'm going to show you the learned dynamics. So basically, a key highlight that I would like to make here is that our learned dynamics do not depend on the knowledge of the ground truth state of the robot. This is what happens for all the other baselines that are out there using learning to predict model dynamics. But actually here we only rely on thrust measurements or commands and gyroscope linear velocities from a gyroscope. Here then we use a temporal convolutional network to process these measurements and then to predict a residual thrust. As I mentioned before, this residual thrust includes learns complex aerodynamic effects or, for example, systematic error that we might have in the calibration of our robot. Then this residual thrust is added to the commanded or the measured thrust and then propagated together with the gyroscope measurements to predict the delta velocity and position of the robot. Here we compare our learned dynamics against the state of the art. Again, I would like to highlight here that all the baselines that you see in this table needs to have access to the ground truth robot state. Here, as you can see, we basically outperform all the baselines but NeuroBM. However, NeuroBM is a great tool for simulating your quadrotor if you want to tune planning and control algorithms, but since it relies on the full ground truth quadrotor state as input, this cannot be used inside a BIO system. So next, I'm going to show basically how our method can improve accuracy of the trajectory estimates. This happens especially at high speeds. As I mentioned before, this is when the aerodynamic effects are actually relevant and need to be considered in the quadrotor dynamics. So here, this table is from the Blackbird dataset, and you can see that the main increase in trajectory estimation accuracy is in the fastest trajectory. Actually, here in the last column, you see HDVIO star. This is our method that has been trained with the speeds up to 2 meters per second and then deployed to trajectories that have speeds that go up to 8 meters per second. This is to highlight that our method does not, our method can generalize to unseen speeds at training time. Next, this is a video where we use 3 industrial fans that blow wind at the quadrotor. The quadrotor is equipped with a drag board. This is to amplify the effects of the wind. And then we show on the bottom right the wind force estimation, and on the bottom left the trajectory estimation. Here I refer to the paper for more quantitative analysis of these experiments. To conclude, so in this work we introduce a novel method to model the quadrotor dynamics and then to use them in visual inertial odometry. So our method is based on a first principle quadrotor model that is augmented with the learned-based component that only relies on measurements. So thank you, and I'm happy to take any questions if there are.
I don't know if this microphone works. I have a question. Now that you have both visual factors and dynamics factors, could you imagine learning both, or having kind of the dynamics factor contributing to improving the camera model, or the camera model contributing to improving the dynamics model?
Yeah, actually, this is a very good point. As I introduced this work, like especially like still in this method, the main source of information is the camera. If the camera component completely fails, for example, where you cannot do feature tracking because of, for example, challenging illumination conditions, the robot dynamics will help till a certain point, then the system will fail. So actually, yeah, this is a good point that I've not addressed in this work, but can be subject of future work for sure. Thank you.
So can you say a little bit why 2 meters per second is such a challenge?
No, actually, 2 meters per second is not a challenge. So what I actually here I say that 8 meters per second is a challenge. What I said is that we train on slow speeds up to 2 meters per second, and then we test. We deploy the system to faster speeds that go up to 8 meters per second. This is 8. It's just because it's the fastest trajectory in this data set. It's not. It's because there is a precise number. This is because of the motion blur in the camera, so it makes challenge to do feature tracking. Thank you. Thank you.
All right, thanks everyone. It is time once again for our coffee break and poster sessions. We will reconvene in half an hour at 2:40 p.m. Thanks. All right, folks, I think we're just about ready to get started. So I'd like to welcome our next speaker for this session, Chad Jenkins. Chad is a professor of robotics and a professor of electrical engineering and computer science at the University of Michigan. And he's also the inaugural program chair of the robotics major degree program, which was launched in 2022 for undergrads at UMich. Welcome, Chad. We're looking forward to your talk.
Thank you so much. There we go. Yay. Kevin, I cannot tell you how many brownie points you earned by talking about our robotics major. So there we go. I love it. I love it. So thank you. And I'm going to try to stay on time here. Although I have so much that I'd like to be able to say, but I just need to click in. And I would say, oftentimes we think about mobile robotics and mobile manipulators. I have 2 fetches in my lab, but I think bipedal mobile manipulation is actually going to be one of the next big challenges, one of the next hot things that we're going to do, which is going to introduce all sorts of uncertainty all over the place. So in addition to perception, we're going to have uncertainty in controls and balance. And so our world is going to be filled with uncertainty as we move forward. And, and I would just put this one question here. How do we start to reason about uncertainty that has uncertainty itself? We're going to have many different levels of uncertainty that we're going to have to deal with. And I would make the case that one of the things that I'd like to do is one potential solution is to think about non-parametric inference, good old particle filters and belief propagation that is differentiable, diagnosable, and decisive. And so this is something that I think it could be really interesting. And so, so what does that mean? And I'll try to get to it in this talk as fast as I can and best in 20 minutes. But to just start off, to just give some insight into what this might look like, what is this? What is that? Have people seen this before? Some people have seen it before. No, maybe some people haven't seen it before. Well, let me give you some hypotheses. As we do a non-parametric inference, we put out a hypothesis, and then we'll see what we'll try to get your best guess about what that is. So, is this an old lady? How many people say old lady? Is that an old lady? Can people see old lady? Okay, maybe a couple people see old lady. Is this a young lady? How many people see young lady? A lot of people see young lady. All right, there we go. I'm glad your belief is there. Because we talk about neural networks a lot, is this a cat? No, probably not cat. Nobody's up for cat. Here's another one that might be a little bit interesting. Is it Taylor Swift? Is that Taylor Swift? Could it be Taylor Swift? I don't know. But maybe one way for us to think about this is if we lay it out on our, as these are samples, hypotheses of particular things of this could be a state, we can form a sort of likelihood of what this could be. So when I see this, I see old lady. Right? So if you look at the mouth at the bottom and then the eye, big nose, eyes, and then a sash on top, that's old lady. A lot of people see young lady. So the young lady is looking off in the distance. It's probably not a cat. It's probably not Taylor Swift. But the thing is, if I think about that, that's just my likelihood. But if I think about my doubt, I can pretty much rule out that's cat. But that could be Taylor Swift. I can't necessarily say that for sure that's not Taylor Swift. Maybe it's Taylor Swift in disguise. I don't know if people like Taylor Swift here or not. Liz Olson, who's my grad student who made this, she loves Taylor Swift. Maybe not Ticketmaster so much, but but that's that, so doubt is another dimension for us to think about the uncertainty. And then everything in between is going to be this ambiguity. Right? That's we sort of build off Dempster-Schaefer theory to sort of think about not just the belief of our system and our likelihood, but also our doubt. And we're going to try to build on that as we start to think about the types of non-parametric inference that we do. And so two questions I'm thinking about is, how do we get models of likelihood? So this isn't just some handcrafted thing that we're doing, but also how do we start to account for this doubt that we might have that lets us say that this is definitely not cat, but it might be Taylor Swift, even though it's probably not. So I'll skip that. And so when we think about our standard discriminative inference, our neural networks, they have good recall, they're fast, but they're inexplicable. We don't know what kind of uncertainty we're dealing with. And so I would like to call these systems decisive. These are decisive systems that we'd like to be able to build off of. But if you think about our old-fashioned generative inference, it's robust, it's explainable, but it's slow. And that's oftentimes why we don't use it. And so, but I would like to call these types of systems diagnosable. We can get in and we can understand what's going on in that system and be able to diagnose what's happening with our particle filter or non-parametric belief propagation. And a lot of what my group is trying to do is trying to get the best of both of these worlds partially by making generative inference less slow and more competitive with discriminative neural network-based inference. So we're trying to bring both of those together. One thing that we do is we can model our problem as a Markov random field or a factor graph. And so if we're trying to perceive, let's say, parts, let's say a robot is in front of it and it has a collection of a collection of objects that are articulated, we can break that object into individual parts and do estimation on each of those parts, and then try to reconcile through messaging how these parts can interrelate to each other. And so this is kind of the approach we've been taking. What we use on the front end is a neural network. So this is actually from pre-pandemic, from 2020. And so we can use a neural network to give us a heat map over possibilities for objects that are on the table. And then we combine that afterwards. We use that heat map and we do a non-parametric belief propagation over it. So we can maintain a bunch of different samples, a bunch of hypotheses, and then evaluate how likely each of those are. When we take the estimate from that distribution, from our estimated distribution, then we can get the likely pose of that part, and then our robot can come in and do manipulation actions off of that estimated state estimate. And so that tends to work pretty well, but this is still sort of using a hard-coded model for likelihood at the end of the day. And so what we presented here last year is something called differentiable non-parametric belief propagation that my student Anthony presented and did a great job. And he basically said in the past, what we had was belief propagation with hand-coded potentials on likelihoods, on inter-node compatibility. And oftentimes that's sort of been discarded and we use neural networks to do everything end to end. But can we get the best of both by having a sort of differentiable neural network-based approach to learn the likelihoods while we're still doing belief propagation, building on great work for differentiable particle filters from Oliver Brock's group. And so this is this is just a pointer to the work from Oliver Brock's group. I'm just showing this to say that many people have thought about these types of ideas. And I'll just show a couple of examples that Anthony had from his paper. And so one was just a sort of simple toy problem here, where we're going to be tracking. So just a simple double pendulum, right? And we want to track this. This object and its relative parts. And as the pendulum moves around, hopefully it moves around, when there's no inclusion, there's no uncertainty. And so the entropy of our particles, of our distribution, stays pretty close. And so we can tell that we don't really have uncertainty in our inference. But when there's occlusions, and the arm goes through an occluding block here, we can look at the entropy of the distribution from our DNBP and see that we have uncertainty. There's many different hypotheses that could account for the potential state. And so this one thing that's great about belief propagation is it extends out to higher dimensional spaces. So a double pendulum, should I really be showing a double pendulum as a state-of-the-art result? Well, yeah, maybe, but I think what's actually really interesting is we took a hand tracking data set. So your hand has many degrees of freedom, and it's so tracking this can be quite complicated. And so what DNBP was able to do was both learn a likelihood from this data set online and be able to track the high dimensional pose of the hand, that it was competitive with, at the time, LSTM networks. And so we can get a good estimate of the belief of possibilities. We can hone it down to a DNB pose estimate in this high dimensional space, and it works pretty well. And so this is something that we think can work work even further as we go along, which I'll sort of talk about. In this sort of whirlwind tour, I'm going kind of fast. So let's assume I can do differentiable inference with non-parametric inference, and that can get me some model of likelihood that comes from the data, comes from the experience of the robot. But now, how do I account for doubt? This is only telling me about my likelihood. I want to be able to factor in negative information about things that may not make sense. And so what we're going to do is we're going to actually consider doubt to be a counter-hypothetical likelihood. So something that's saying this most likely is not true. And so what we're going to have is that counter-hypothetical, the counter-hypothetical likelihood, the likelihood, and then what remains in between is ambiguity, just what we can't say about our system. And so we'll start off by talking about the counter-hypothetical particle filter. Please keep me on time. I will go for as long as you let me go. So if we go back to our favorite hallway example, when I was a young graduate student, I was amazed by the Frank Dellerts and the Dieter Foxes and Sebastian Thrones of the world, and I learned probabilistic inference through the hallway example. And so our good old fashioned particle filter, basically maintains our samples. We make predictions about the world and how they occur. We measure how well each of those hypotheses accord with the actual world. That gives us our likelihood, our measurement, and then that gives us a posterior. But the problem is that we can get mode collapse. We can collapse into various modes if we don't have particles that are sampling in the right location, in the right areas of state space. So this particle deprivation problem can lead to mode collapse. And so building on these notions of, one thing that you can do that we always sort of tend to do with particle filters, we have some sort of reinvigoration process. We use some set of our particles and we kind of say, all right, we don't necessarily trust our likelihood. We're going to just throw some particles out and maintain states that may not be represented in our distribution. And so that might be some sort of candidate distribution. A number of people have if you've AMCL, there's a number of different approaches to doing this particle reinvigoration. We build off of Lenzer and Veloso, which says that there's sort of a estimated max likelihood that you might think about, and then based on how likely your particle is, your hypothesis is, you can sort of estimate your doubt based off of that max threshold, which you get somehow through magic. But once you do that, then you have you can build off to get a counter hypothetical particle filter, where you can adaptively figure out the number of particles that you can give to your candidate distribution as sort of a null hypothesis. So if you're very certain about what you like, or what the state is, then you don't have to use a lot of this candidate distribution. If you're uncertain, you're just like, I've got some belief, but I'm not sure, is it Cat, Taylor Swift? I'm not sure. So let me dump more into my candidate distribution. And this sort of gives us a way of thinking about it. In Lenzer, what they did was they looked at the proportion of your likelihood over the number of samples. And so just the high level of math here is that we've sort of broken down their denominator into a likelihood term and a counter likelihood term, a counter hypothetical likelihood term. And this just gives us a better way of being able to figure out how many samples do we want to get to our candidate distribution versus believing our belief on our likelihood. And so this tends to work out pretty well in practice. This allows us to break up some symmetries. So if you think about, if we compare to like Posar BPF, what you'll see with this is that the banana that we have right here, the banana is actually flipped 180 degrees. And so once the particles mode collapse onto that incorrect result, it has a hard time getting away from that incorrect hypothesis. But because we use a counter hypothetical particle filter, we're able to say, maybe that's not right. Maybe this is saying Taylor Swift, and it's actually, this is saying old lady, but it might be young lady. And so let's throw some more of our particles out, and we can actually find this true estimate. And so this is the case of breaking that symmetry with the banana. Showing a little bit more YCB data set. This is us basically figuring out. All right, we're not showing that video. That the bowl for our Posar PPF, which is fabulous, by the way. It can't quite get the right flip, the right orientation, because it's stuck in a mode collapse. But our counter hypothetical particle filter is able to do that. This is just showing that occlusions are hard. Our success rate is around 65, 70%. Which is better than most. Still, we've got a ways to go in this area, but our initial results against what we saw as the state of the art, it's pretty good, pretty promising. So the last thing I'll talk about is how we build on that counter hypothetical particle filter to do counter hypothetical non-parametric belief propagation. How can we extend this out to high dimensional spaces? And so to do this, Liz continued her work and developed what was called wager DNBP. So it's building on differentiable non-parametric belief propagation. We go out and we get estimates on each of the individual poses of, let's say, a high dimensional structure like a digit robot. And then we use the similar sort of adaptive reasoning, counter hypothetical reasoning to get a pose estimate. One thing that, so many people have contributed data sets that do high degree of freedom pose estimation and tracking. We're going to contribute another sort of data set too. So we're going to have the digit walk around, and we're going to try to put lots of inclusions in front of it. So we're working on a data set now that really has this high dimensional, high degree of freedom system, and then be able to just introduce all sorts of weird occlusions to try to see how well our system can work, that combines non-parametric belief propagation and differentiable inference. I'm just not going to go through that, but it's a lot of the same ideas. So that's our methodology. When the paper comes out, you can take a look at that. But I'm gonna skip that. But if we compared with DNBP, which is on the top right here, which has a hard time which can work, but we're having a hard time dealing with those occlusions because we're not getting stability there. Our wagered DNBP on the bottom is able to get a good, reasonable estimate. So the belief is able to converge around around roughly the true state of the robot. It's not quite perfect. It's still off by maybe about 10 or 20 centimeters, per element, but it's getting there. And the fact that we're learning that likelihood is really encouraging. Before I go, how am I doing on time? Did I speed through this? 2 minutes. All right. All right. In our remaining 2 minutes, I have one more question. What's the best undergraduate major to become a roboticist? Kevin Doherty, what's the best undergraduate major to become a roboticist? For robotics, absolutely. If you want to know I actually have a more funny answer than that. You'll have to come and see one of my other talks to see that. But yes, we've launched a robotics major here at Michigan. It's one of the first, building on great work by the major at Worcester Polytech back in 2008, 2009. We've launched our first robotics major in recent years. It's designed to really define the discipline of robotics for both equity and excellence. Robotics is becoming its own academic discipline, and the thing that really makes an academic discipline is its undergraduate program. That is how we teach and give people the perspective of how to become a roboticist. If you're a geology major, you see the world through geology. If you're a computer scientist, you see the world through computer science. That doesn't limit your perspective, but it gives you a foundation for knowledge throughout your life. And so we launched this 1 year ago to define the discipline of robotics, innovate for equity and excellence, that got cut off excellence, but also meet the emerging needs of society. Students, or if you're in a computer science program right now, we're packed with majors. That's because people are looking for AI and robotics and they don't necessarily know where to go. And also industry is asking for this from us. So this is a big deal. In our first year, I would say that we went from, in our first 1.1 semesters, we accelerated from 0 to 60 majors, declared majors in 1.1 semesters. We're at 112 majors right now. Those are our first 2 graduates. You can probably see them walking around IROS. And so we're really excited about that. If you want to know more about our undergraduate program, you can check out our paper on arXiv that has all of our degree details and a little bit of foreword from me to give some context, which actually has the answer to that question if you want to read it. I just want to thank everybody for their time. I'd like to thank Anthony Opapari, Jana Plavlasik, Liz Olson, and now Professor Karthik Singh. Thank you very much for listening.
Fortunately, don't think we have time for questions, but please track down Chad and chat about non-parametric belief propagation and undergrad at UMich in robotics. All right. Thanks, Chad.
Thank you.
Alrighty. Our next speaker is Katie Skinner. She is an assistant professor in the Department of Robotics at UMich. And she also holds a courtesy appointment in the Department of Naval Architecture and Marine Engineering. Welcome, Katie.
All right, thank you for the introduction. I'm really excited to be here to talk about my work in mapping and perception for field robotics. And I'm hoping to use this talk to give some perspective on some of the challenges we've been thinking about and the opportunities that I see for the field moving forward. So field robotics refers to anytime we put robots out into dynamic, varying, challenging, typically outdoor environments. This can be applications across air, land, sea, and space, including autonomous vehicles. And we have a lot of challenges to perception when we put robots into these challenging environments. We have a lack of ground truth labels, for example, which can limit our ability to transfer success of machine learning algorithms from indoor applications to, for example, underwater applications. We also have a greater need for generalizability because many times we're putting robots into places we have never sent them before. So that really requires increased need for generalizability. And typically we deal with sparse and very noisy data. So I'm not going to touch on all of these today, but I just want to highlight a couple of challenges and some of the solutions that we have been thinking about. So one of the areas of my research is marine robotics. I think marine robotics is a really exciting field because it enables us to explore coastal environments, our Great Lakes that we're surrounded by here in Michigan, and the deepest parts of our oceans. So there are, of course, many challenges to operating robots in underwater environments, including just general operational issues that we have with varying weather conditions we have to battle. But we also have technical challenges and fundamental limitations. We don't have access to GPS underwater. We don't have access to Wi-Fi. So we really need to think about creative solutions to dealing with these limitations. And autonomous vehicles underwater must really be equipped with the tools and perception needed to process the data that they're collecting on board as they are navigating their environment. Of course, the data that we see underwater typically looks much different than in air. If this video will play. So here is an imaging survey from an ROV from recent fieldwork my group did in Thunder Bay National Marine Sanctuary. This is the Monahans shipwreck site. And you can see right away that the images that we get underwater are very different than what we see in air, right? So we have this distorted color, we have some interesting caustic lighting patterns, and as we start to look further and further away from the camera, we also have haze effects across the scene. So we need to think about ways to overcome some of these fundamental differences that we see in underwater environments. And we've gotten pretty good at doing that over the years. So we can collect a lot of underwater imagery and use this imagery to create large-scale, metrically accurate 3D reconstructions of underwater scenes. But it's still not quite what we would want, right? So this 3D reconstruction was one of the best that we got from several weeks of fieldwork. It took several days to compute, so it was fully computed offline. And you still see a lot of the distorted color that we collect in underwater imagery. So that can also lead to artifacts and floating structures as well. What we don't see here, but what is also very common is holes and sparsity in 3D models that we're able to compute. And I think it's helpful to think about why we have these challenges. So we can look to the model of underwater image formation to see why they occur. So as a particle of light travels between light, the scene, and the camera, it interacts with particulate matter in the water column that leads to scattering and absorption. And absorption leads to attenuation that is wavelength dependent and range dependent. So if we were to image something in air, it might have a wide variety of color. But if we image that same pattern underwater in ocean environments, you would see that the red channel, for example, is attenuated much more quickly than the blue channel and the green channel. Backscattering leads to this haze effect across the scene. It's very similar to fog in air, and it's also range dependent. So as you get further away from the camera, you see increased fog or haze activity. And the reason why this is important is because it has several consequences for computer vision and robot perception methods. So one is for feature detection and matching. Because of that attenuation, we typically have much more reduced contrast for images that we collect underwater. So if we were to image, and this is from an artificial rock structure, one feature in air, you could see very high contrast, which we would use for feature detection. But that same image patch underwater has much more reduced contrast, which already challenges our methods for feature detection. It also leads to a breakdown of assumptions that we make on land for photometric consistency and brightness constancy. So if you image a viewpoint from one point of view underwater and then move to a different perspective at perhaps a different range from the scene, it can look quite different in appearance. And this breaks down those assumptions that we use, especially in direct SLAM methods on land. So these are some of the challenges that we have been thinking about, and one potential opportunity I've been really excited about is NERFs. So I'm sure that a lot of you have seen these results already and been impressed with kind of the power of NERFs to represent scenes with very dense volumetric implicit representations. So with a sequence of images, typically a 360 view of an object, we can learn to reconstruct both structure and also perform novel view synthesis of many complex scenes. So we have started to think about how this might be useful for our underwater environments. And we recently published water nerf neuroradiance fields for underwater scenes to take a stab at what this might look like. So for water nerf, we leveraged depth estimates from a MIP nerf architecture and incorporated the model of underwater image formation to both learn to take the depth estimate from the NERF network and parameterize a model for underwater image restoration, because we think the implicit representations should not necessarily represent the raw underwater imagery, but also be able to allow us to recover what that imagery would look like if taken in air, right? We want to learn the true structure and color of the scene ultimately. So with this method, we were able to perform novel view synthesis and image correction in order to recover what that true underwater scene might look like. And we were pretty happy with just our first results. So we can perform novel view synthesis to recover accurate color, but also consistent color across different viewpoints. And we're also able to recover dense structure as well. And using this dense structure with just one single depth map output from the network and one corrected color image, we can project this view into a very dense 3D model of our underwater scene, which is pretty exciting because dense reconstruction underwater is a pretty challenging task. So I'm really excited about the potential for NERFs to learn a dense volumetric representation, and I think we've seen this proof of concept that this could be really powerful and useful underwater. There's potential to incorporate the model of underwater image formation into NERF architectures, and that can allow us to get a better understanding of these effects that we are seeing. Of course, some downsides. The computational time to train these models is still quite large. And at the time we did this work, many NERFs still required images from multiple viewpoints around an object, which isn't very representative of what we see in robotics applications. And beyond that, they're typically challenged by large unbounded scenes, although this is getting much better with recent models. So we started to think about how to address some of these challenges and moved to the autonomous vehicle space to do so. So this led us to Cloner, and Cloner looks at incorporating both camera and LiDAR data from sparse viewpoints in order to perform NERF reconstruction. So Cloner takes as input just an input stereo pair and a sparse LiDAR point cloud and learns to output a dense map of the scene as well as novel view synthesis and a learned occupancy grid. So this was really our first stab at trying to leverage sparse data that we might collect initially when we turn our robot on or start moving along a trajectory and see if we could use just this sparse and noisy data to leverage the power of NERFs. And there were a couple of things we needed to do this. So one is we noted that the depth estimation that we get from the LiDAR, depth measurement that we get from the LiDAR can be really useful for helping to guide our training. So we actually use the LiDAR data to learn a 3D occupancy map. And this 3D occupancy grid is used for important sampling for the NERF itself. We also used a decoupled NERF structure, so the RGB is learned separately from the structure. And in that way, the structure is really learned only from the LiDAR, but the RGB MLP is considering the learned occupancy grid to learn the color as well. And here are some of our results. So we can see that just from 2 sparse input views and sparse LiDAR, we were pretty happy with the smoothness that we're able to see across the scene. We can reconstruct some thin features and some complex textures. Of course, there are some holes, especially in the sky, where we don't have LiDAR returns because we're using that LiDAR data to learn the structure. But overall, this is pretty promising for being able to leverage only sparse data that we might collect on board our robots for nerve reconstruction. So we can learn this dense volumetric representation from sparse data. We're also able to handle varying lighting conditions. We tested our method on the kitty data set, so we see a lot of overexposure, shadowing effects, and we seem pretty robust to these. For depth estimation, we can handle sparse input viewpoints, and we can operate in unbounded scenes, although again, we don't learn the sky locations. And again, one limitation of this was still that we were training offline, right, which isn't very realistic for robotics applications. So this led us to think about how we might start to use nerve frameworks in online fashions. And we recently released Loner, which is LiDAR-only neural representations for real-time SLAM. We're not very creative with our names, so they all kind of sound the same. But Loner allows us to take in sparse LiDAR data and learn an implicit model for the structure representation while performing SLAM online as it's moving throughout the scene. So this is an example of a mesh that we could reconstruct offline with novel views that we can then render at any point in the learned volume itself. So Loner really follows a traditional SLAM framework, but incorporating nerve architectures for learning structure. And some of the key insights we have here really are with the novel loss function that we designed for the mapping component. So our loss function is an adaptive loss that sets an adaptive margin for considering individual rays. So it sets higher margins for rays in unobserved regions to improve convergence and lower margins for rays in learned regions to refine learned geometry. And with this adaptive loss function, it can really allow us to reduce the computational time needed to train nerve models. And this is what allows for the online component. Let's see if this video will play. Oh, here we go. So here's, again, just an example of rendering dense depth maps that we learn as we move throughout the 3D model or the 3D volume. And we're starting to test this in a couple of different environments. For now, we have contained it to indoor-outdoor scenes that are a little bit more contained, more for memory constraints. But this is one thing that we're looking towards improving in the future to be able to go into wide open areas for working in those larger unbounded scenes. But overall, what this taught us is that we can, again, learn a dense volumetric representation of our environment. We can handle varying lighting conditions and sparse viewpoints, and we can formulate this in a way that allows us to perform online SLAM and also learn an implicit neural representation of our environment. Of course, the downside of Loner is because it's only using LiDAR data, it actually doesn't learn any RGB information about the scene, so this is one thing that we're excited to work on for the future. So I hope that gives you an overview of some of the challenges that we've been thinking about in terms of applying recent successes of NERFs in computer vision to applications that we could think about deploying in the real world for robots across different applications in field robotics. So I just want to thank my students and my collaborators and sponsors, and I left my email up here if anyone has any questions as well. Thank you. Yes, I think the question was, what is the advantage of using NERF over traditional methods? So I think the potential that I see is really in the ability to learn a really dense representation of the scene. And this is what I see as being something that would be really impactful for mapping in environments where traditional computer vision methods fail, right? So if we think about the underwater case, we need to figure out how to deal with the water column effects that we see. We need to deal with featureless regions and with complex features. And I think so far from what I've seen, I think NERFs would be a really great tool for addressing some of those challenges. But there's, of course, a lot of work to do. So hopefully that will give you some inspiration to get started.
Is there any advantage over classical ultrasonic-based device such as digital sonar?
Oh, sorry, can you repeat?
If there is any advantage compared to classical device for underwater, such as the digital sonar, ultrasonic-based imagery for resolution?
So compared to using like imaging sonar for reconstruction, so sonar is still quite sparse in terms of what we're able to observe underwater compared to the dense models that we might want to use, for example, for science applications like shipwreck monitoring or coral reef monitoring. And for some of those applications, color is really important as well. So being able to learn to map the color onto the structure is something that we want to be able to resolve too.
Do you think that imaging sonar or any other sensors are a good like analog for LiDAR in the underwater case if you were to use like a cloner or another thing?
I'm not sure about analog, but I do know that there is work that has been done or started looking into NERFs for sonar, and I think that's a really exciting avenue as well. I think looking at different sensor models and how we can leverage NERFs to not just learn to model those sensor measurements, but also maybe fuse different sensor measurements could be really exciting field too.
Yeah, actually to train their visual utilize a close structure promotion, such as whole map to trainer, but in underwater environment, images are easily corrupted and degraded. So what is your recommendation if image is too degraded? So there's no abundant feature matches to train the nerve, then what is your recommendation to overcome that?
Yeah, that's a really good question. So for our water nerve paper, we were using a small size data set collected in a water tank. So it is a bit of it kind of simplifies the problem, and we were able to use COMAP to get ground truth poses for that structure, but applying it to larger scenes, that was a challenge. So what we did with Loner that I think can maybe provide some ideas is we were performing SLAM, so we're also estimating the pose using, in this case, ICP registration from the LiDAR. But I think maybe that's something we could think about leveraging underwater as well. If we're performing state estimation too, how can we use that to initialize our NERF models? Great, thank you very much.
All right, folks. Well, we've made it to our final talk of the session and, in fact, the workshop. Our last speaker will be Sai Vemprala, who is the co-founder and CTO at Scaled Foundations, an AI research and development company. Welcome, Sai.
All right. Hello, everyone. Thanks so much for the invite. I'm really excited to be here and giving this talk. Lots of great discussion so far on foundation models and the future of robotics, perception, and planning. So, well, hoping to contribute a little bit to that. So I don't think I'll have to motivate you so much on the promise of foundation models. I think we've had a lot of discussion on that already, lots of great points being made. But I just want to recap it a little bit, that the way we want to believe in the promise is that there needs to be a broadly adaptable kind of a platform and architecture that is pre-trained on data at scale, similar to the GPT or the vision, the pre-trained large model that we were seeing. And it needs to be able to accelerate the infusion of intelligent capabilities onto robots, right? So, but we also know that in the mainstream machine learning kind of point of view, the extent of multimodality has been, vision and text for the most part. But of course, we know that robotics has a lot of diversity in the form factors, in the sensor modalities, in the kind of noise patterns, constraints, and of course, last but not the least, the paramount importance of safety. So then the question becomes like, what will a foundation model for robotics look like? And then, there has been several attempts at answering this question. And I'd like to take you through our way of thinking what robot intelligence should look like and what we've been trying to do to get there. And some of the past work that I've been involved in started to look at this idea of general purpose representations, right? So we started off with a perception only kind of representation point of view. For this work, which is called Compass, this is a multimodal pre-training kind of a problem where we try to combine multiple modalities such as RGB, depth, segmentation, and optical flow into a common representation space. And we use the Tartan-Air dataset for this, which is a large unstructured kind of multimodal dataset. And we were able to find that this representation could be fine-tuned for robotics tasks such as drone navigation or a car like racing on a track and things like that and trying to behave safely. So we found out that there is potential in multimodal representations and they can be fine-tuned fairly quickly compared to something that's trained from scratch. And then we moved on to thinking about, okay, what about perception action combined? So PACT, which stands for the Perception Action Causal Transformer, was an attempt at that. And this is kind of like the decision transformer point of view where we said, take massive data sets of trajectories which are composed of observations and actions, and we pre-train a large transformer model on these sequences, and we try to regress to the safe action. And similar to if you take an analog to GPT, it's been trained on massive amounts of text, which is all incidentally grammatically correct. So at the end of the day, it might make semantic mistakes, but it never really makes grammatical mistakes as much as possible. So similarly, we find out that an architecture training like this, it can regress to a safe action, and it behaves like it just rolls out safe policies as much as you drive, well, as much to a certain extent. And it also implicitly encodes features which are useful for things like localization and mapping. So there are a lot of things that are happening implicit to this representation. And this is already fusing, the state action transitions and a notion of a dynamics model representation. But of course, intelligence is a loaded word, right? So even the previous works that I just talked about, you will have to kind of fine tune them specific to a task, or maybe you'll have to, in the case of PACT, we were actually training this on a per robot basis. So then the question becomes to be just create a massive data set of multiple embodiments, maybe similar to the RTX kind of work that we've seen this week, and use that as a starting point for doing some intelligent tasks. But I want to come up with like a little hypothesis here. So the definition that we are trying to come up with for robot intelligence is that the ability of robots, plural, to learn, compose, and adapt skills to their physical capabilities, their own constraints, and their own goals. So this is again taking the GPT sort of a perspective where there's a lot of emergent behavior in the model, and it's being applied to software development. It's being applied to so many creative tasks in programming and just reasoning, and even in robotics, as we'll see. Right. So is there an architecture that can be a starting point and that can take robotics developers, for instance, like 70-80% of the way in terms of creating some intelligent behavior? And a sub point in that is that the focus really, when it comes to this notion of intelligence, is more on the planning, the long horizon kind of planning, and the reasoning and the decision making and uncertainty. And these are all things that for example, language models kind of seem to shine at. Right. So I'm deliberately removing things like control from this conversation. So because I'm not saying that end-to-end control is probably the first thing that we want to tackle as part of a foundation model like this, especially because for some form factors, at least, like wheeled robots or drones, normally flying drones, not super agile drones, control is fairly well solved. So if we can make use of the existing control stacks and the architectures, can we place the focus on more of these hard problems that are still open questions? So we can imagine that what we expect from a platform like this or an architecture like this is considerable zero-shot ability. So it needs to be adaptable to many different kinds of environments. And most importantly, it needs to do multiple things fairly well, as opposed to being an expert at one single thing and having to fine-tune it for different tasks. And in a work that we did early this year, which is called ChatGPT for Robotics, we noticed that large language models actually show a lot of promise as mainly orchestrators, as well as, sort of like common sense or reasoning agents. So you might have seen in the initial part of this GIF, but we asked ChatGPT, and this was GPT 3.5, this was before GPT 4 came out, and we said, hey, I want you to, there's a robotic arm, and I'll give you all the API of this robotic arm, and I want you to arrange blocks in the shape of the Microsoft logo. And we did not even describe what the Microsoft logo looked like. It actually knew it from its knowledge base, I guess, and it was able to, pull that off with not a lot of human input being required. And similarly, we did the same thing for a drone API, and we said, there is a shelf in front of you. I want you to inspect in a lawnmower pattern. And it kind of understands that it means that there's a sweeping motion that needs to happen. And similarly, we can also use it for sort of embodied AI kind of tasks. When we pose questions like, I want you to, go find a place where I can warm up my lunch, and it knows I'm talking about a microwave, and then it's able to control the robot appropriately. So is that all? Obviously not, right? Because, there are several things that large language models still don't understand, and especially when it comes to a holistic understanding of the scene and the world. We are interested in things like 2D, 3D kind of like correspondences and grounding. They don't necessarily have like a good spatiotemporal sense, especially when it comes to robot safety and what are the results of certain motions or the causality of it all. So again, they're not like one size fits all kind of solutions. And especially in robotics, we have way too many sensor modalities, and we also have information modalities. By information, I mean, things like bounding boxes or segmentation masks or locations, all this kinds of stuff. And lastly, there is a massive diversity in the action spaces. And for those of you who might have seen papers like DeepMind's Gato, for instance, they go through some interesting schemes of being able to tokenize different actions for different robots so the model can have an understanding of it all. So the pipeline, we can think of it as something that looks like the figure below. So there are sensor modalities, there is a notion of extracting the right kinds of features, and then there is a planning aspect of it, and there is the execution and control. And if we look at those 2 points, the multiple modalities and the extreme diversity in action spaces, it is possible to obviously fuse different kinds of information into a representation, right? So you can probably use synthetic data. You can find some way to get multiple sources of information of what's happening in a scene and try to pack it all into a common representation, similar to maybe what we try to do in Compass. But it is a very compute-heavy problem, and there's a lot of sample complexity there. So the question is, obviously, we have a dearth of data in robotics use cases. So what we are proposing there is one solution which will at least alleviate some of the sample complexity problem, which is let's use existing foundation models. Because as we looked at earlier in the ChatGPT work, they are very good orchestrators. They're very good users of tools. They might not be able to do everything, but they know how to chain existing methods together in a way that makes sense. So by pulling in all the work that's been done in computer vision space for detection, segmentation, foundation models like segment anything and so on, we already have like a very rich bank of models that can extract immense amount of information. And I'm actually continually surprised by how good VQA models are getting, day by day, right? So even if LLMs are not able to do it by themselves, maybe GPT-4 Vision is an exception because it can look at images. But there's a lot of other kinds of data that we'll have to pull in. So we can use existing foundation models. So that's the first thing. And the diversity in the action spaces problem, like how do we teach the model like all these different kinds of actions? How do we tokenize them? What's the shared abstraction? Well, let's not worry about it. Well, let's rely on existing controllers. And again, if we can ask the LLMs to write code which is controlling the APIs of these different kinds of robots, this is, again, a zero-shot kind of a capability because they can adapt and understand what these API calls are really doing, and then they will chain them appropriately based on your task of interest. So in a way, I think the tokenization scheme, so to speak, here is actually in the form of code or text. Like everything is feeding into this common language kind of token space, and even the outputs are really not, you're not regressing to actions, and you're only regressing to a very high-level abstraction representation, such as a call for a position set point or a trajectory or something like that, which can hopefully be very robustly executed on the robot. So to that end, we actually recently put out a vision paper just 2 days ago. I'll provide a link towards the end. But we are trying to develop a platform that we are calling GRID, which stands for the General Robot Intelligence Development. And the high-level pieces of that are really what I just talked about. So at the middle lies an orchestration layer, which is powered by language models. And then it's been given access to what we are calling a foundation mosaic. And this is a collection of tools. I mean, this can be obviously all the state-of-the-art foundation models in computer vision or any robotics relevant tasks such as visual odometry or positioning and anything that we believe is task relevant it is as easy as essentially specifying like the doc string for the API of these models, and you just toss it into the LLM system prompt. And if we blow it up a little bit, so we have on the left, we have these collections of models which are useful, which can do a lot of interesting things in the domains that we care about. The orchestrator is mainly powered by the language model. And there are multiple ways of looking at how this orchestration works, right? So for instance, we can still think of a notion where all of these models are outputting some features, and they are all being tokenized, and they're being combined with the language, and it's going into the language model. But to start with, we don't even have to train it that way. We can start by saying the LLM can just be a selector. It can just select the right kinds of models, call them, grab the outputs, make sense of it, maybe translate them into language, like for example, in a VQA kind of a sense, and essentially output code at the end of it, which can run on the robots. And so the way this platform would typically work is that the user could provide an instruction, and then the LLM would try to choose which models make the most sense given the robot API and the perception, like, sensor capabilities that the robot has, output some code. And most critically, I think there is a very key role a simulation can play here. Right, so the code, for instance, can be deployed on a real robot, of course, if one were to be that brave. But probably a better thing to do would be to run this in simulation and use that feedback and send it back to the model and then have it kind of refine its own output. So this is on the LLM side. So again, there is a lot of interesting work happening in what people are calling these multi-agent LLM architectures. So there are multiple LLMs working with each other and also refining themselves based on some external feedback. Usually it's in the form of, like a web browser output or something, or in the case of ChatGPT, it's been RLHF with human preference information. And, we don't even have to do human references because we have simulation environments. And hopefully these simulations have enough ground truth that they can teach the LLM what it's been doing wrong and, where things might have gone wrong or something like that. But at the end of the day, running in simulation allows us to propagate some feedback back and then refine the LLM. And if we have the resources, even fine-tune the LLM over a large database of it. And also fine-tune the models if we need to, if there is like a very specific scenario that might have been in the distribution of the perception models. And yeah, just to reemphasize, there is a very interesting role that simulation kind of plays, and we have the possibility of looking at a simulation equivalent of RLHF. But at the same time, we don't have to necessarily fine-tune. One thing that we found in our experiments is you could essentially have the LLM treat the simulation as a sandbox, play with it on its own with minimal human intervention. And once it figures out what's the right way to solve a task, it can actually create a skill for itself. So it can re-encode all the steps that it did as part of essentially like a text file. And then whenever this architecture is supposed to reuse that skill, it can just read it back up. And it's able to reuse it. And on the videos here, I'm actually showing, some of you might be familiar with AirSim, the aerial robotics simulation. So we are actually creating a new version of that, which we're calling AirGen. And this, again, the focus of the simulation is for aerial robotic scenarios to have a wide variety of environments, multiple modalities of sensors, a lot of customization in weather conditions, sensor noise, all of these kinds of things. And also, interestingly, we've fused this with Google Maps recently, so we can actually fly the drones in pretty much any real city. And we also have inbuilt mapping and navigation for ground truth if somebody wants to train, like an intelligent agent in there. All right, so what can this architecture do? I mean, sure, this is it's an exciting possibility that we have access to several models as part of it. So I want to take you through a few examples. So, for example, in this case, the user, well, that was me, I provide an image of this. This is a simulation scene being looked at like top down from a drone. And I ask Grid, for instance, I say, I want you to examine this image and tell me if there is a safe landing spot for a drone. And I explain that a landing spot needs to be, reasonably flat and it should be on solid ground, clear of obstacles and so on. And a VQA model by itself may or may not be able to fully answer this question, especially when it comes to the reasonably flat and those sorts of constructs, right? But Grid, considering that's an LLM combined with multiple models, the first thing it does, it automatically realizes it needs to call a VQA model to understand exactly what's going on in the scene. And the VQA model responds by saying, okay, there's a large house with a pool, there is some grass, trees, and a shed. And then the common sense part of the LLM kind of kicks in and says, okay, maybe it's a grass that could be potentially the most reasonable landing spot. And with, again, zero human intervention, it then calls a segmentation model and looks for grass. And then it calls an RGB to depth model. We used Midas for this and grounded SAM, I believe, for the segmentation. And then it uses the depth model to figure out which are the sort of like flatter regions based on the variance of the depth within patches of the image, and kind of computes the overlap between the grassy area and the segmentation and the depth map, and says, okay, the red zone, I asked it to actually draw this in red for me as an output. So it says the red zone is probably where you should land the drone, right? And all of the code that's required for analyzing the depth or the segmentation and everything was all just written by the language model. And for instance, this is another one. I provide this example of an image that I just pulled out from the internet. And I said, compute a metric semantic map of the scene. And I did not even describe what a metric semantic map is. But given the models, I think it kind of makes sense that, okay, it's a combination of, depth and segmentation. So it uses like an open set segmentation model. And again, Midas, and then creates this overlay for me, which I asked it to draw. And then when I ask a question like, where should I go to find the fridge? And I ask it to draw an arrow just, artificially so that I can show that. It actually figures it out. I mean, it's not that hard. Now that you have the full information about the scene and the objects and everything, it's probably not too hard to just figure out from where I am, which angle should I turn, and then how far the refrigerator might be, right? So they're already being equipped with enough information that we can potentially look at solving things like object goal navigation or visual language navigation over a longer horizon. And for more interesting use cases, and specifically to highlight this long horizon planning part, we actually applied this inside of the AirGen simulation, and we tried to pose some interesting problems to it. So we put it in the scene with a forest and a forest fire, and then we started asking questions about sort of like reasoning like questions. So, what do you see? And it says, I see a fire, there's some smoke and everything. But then we ask it, okay, we need to do a search and rescue operation. Where do you think is the most reasonable place for me to start with the drone? And the amount of information it extracts was surprising to me. So it already sees that there is a cliff and there are all the trees. And I did not even notice that there was water in the scene. There actually was. And it says, oh, looks like there's a river. So maybe, people might head there for as a chance of escape or something. And we use this as priming to actually define a full mission inside the simulation. So all of the steps that I'm showing here, unfortunately, I do not have a video yet. This was just done like end of last week. So detection of the fire, kind of like keeping it centered and flying towards it using an object detector, and then creating a search pattern when we ask it to for searching for human survivors, and then flying through the forest using some path planning capabilities and looking and counting the number of people it sees. All of it was really orchestrated just by the model with a little bit of like human feedback, right? So the idea is really that, if you have something in mind, a framework like this should let us prototype it as soon as possible, as quickly as possible. And of course, I mean, it's not going to be perfect 100% of the time, but at least with minimal like back and forth and feedback from the human side, it makes it faster to infuse a lot of this intelligent capabilities. And another thing that we tried to do was in the simulation, we did infrastructure inspection, which is a pretty interesting high value use case in real life. And it's able to use, again, RGB to depth models, figured out some like, how to get a point cloud out of it, how do I get the normals from the point cloud and fly the drone through that by using an off-the-shelf planner. And on the right, I show again some samples on the zero-shot reasoning capabilities of these VQA models. It's talking about what kinds of damage it's seeing on a turbine blade. And this can be an interesting way to even think about for analytics and stuff like that as well. But that's probably out of scope a little bit. So yeah, finally, there's a few more examples that we did, but I'm not going to go through all of them. Again, to speak to the zero-shot capabilities of these models. Again, none of these models were fine-tuned on any of this data, right? And the LLM, obviously, we cannot fine-tune. I think it's too hard. None of the perception models were fine-tuned as well, which shows the use of, kind of going with these capable state-of-the-art foundation models. This is a visual tracking and landing experiment that we set up using a object detector, RGB to depth, and a point tracker. And it was able to work, again, zero shot under adverse weather conditions, even in low light. And this was all probably took like, half an hour to do this entire thing. But yeah, I'll stop here. Hopefully that was a quick overview of all the things that we can do by using LLMs and foundation models together by giving access to tools. And I just want to end by saying that the Grid platform is open. It's in preview and it's free and unrestricted for academic use. So please feel free to take a look, and you can scan the QR code to get to our GitHub. And that's a list of all the open source models that we are currently curating, and we hope to have a lot more soon. And yeah, happy to take questions.
Thanks for that great talk. I want to ask, how do you handle or want to handle memory for long-term tasks. Because as far as I know, these large language models have a not so long context.
That's a great question. Yeah, the question was about how do we handle memory in the case of long conversations. And the way we are actually doing it right now is we are constraining the output of the LLM to be in like a structured format, like a JSON. So JSON takes care of things like, okay, what task are you currently dealing with? And, how many last messages have you kind of like, have you output for this specific task? So that lets us, basically call, old tasks or something like that as we go through the entire conversation. And so we have a notion of memory like that, which is very primitive right now. So we preserve the system prompt, which is all the API and stuff. And we remove, some of these portions of older tasks or things that are no longer relevant. And yeah, the gist is we are trying to structure the output so that we can cut things as appropriate and keep the conversation under a certain limit. Yeah. Yeah.
So for these tasks in the physical world, is SLAM a module of it that it uses?
It definitely can be. If there is a way for us to already, get a map and a localization for your robot, and yeah, I mean, there's no reason why that cannot be a module as well.
Thank you.
Yeah.
That's all the time we have.
Okay. Wait, we can probably chat later. All right, thank you so much.
Just whatever.
Yeah. I think Kaveh is going to do some closing remarks briefly, but those of you who have questions for Sai, please track them down maybe after Kaveh.
All right. So I'm not going to keep you here long. I know it's been a long day, but very, very productive, very exciting. So I just wanted to capture my take on the workshop on the day. I think it was a pretty exciting workshop and the amazing series of talks, thanks to the invited speakers and panelists that accepted our invitations and came here. I think we really covered the impact of some of these frontier vision learning techniques like LLMs or NERFs on robotic perception, and there's some very interesting open questions that I think we can pursue for the next 5 to 10 years or so. The poster sessions outside, I think it was quite successful. So I saw a lot of people gathering around the posters and asking questions. The panel discussion was great, and we have way more questions than we could even sort of attempt and hope to answer them and ask them. Lastly, I want to mention that we've been recording the talks, in case you've noticed, and we're going to process the videos and put them up on YouTube in sort of shortly, but maximum 2 weeks, right? So if you want to see that YouTube video, just go to the workshop webpage, and it's going to be just in the top of the webpage. All right. So I want to thank all of you, first of all, for just being here, attending the workshop, making it successful. I want to thank all of the authors, people who contribute to the workshop, created the posters, and our speakers and panelists, of course, and our workshop committee and chairs. So this was not possible without their help of getting everything together. So I'm very grateful for you, very grateful for our chairs today. And before you go, so this is the last slide, I just want to ask you for feedback. So we are thinking about organizing, say, another workshop, maybe in ICRA 25, which will be in Georgia, Atlanta. And your feedback will be very appreciated. So just scan this link, right? So go to this link, leave your anonymous comments, tell us what you think worked really well in this workshop. If you organize that sort of follow-up workshop, what are the things that you would like to see, any changes, differences, and such. And with that, I want to close our workshop today. Thanks again for being here, and have a great weekend.